So, hello everyone. My name is Daniel Müller-Kritschneder. I am the professor for real-time computer systems here at Technical University of Munich. And I will teach you some part of this class which is very deeply related to the embedded processors and how they work. And this fits very well together with what you have already learned from Alex, who told you like how C code works, how you can run C code on top of an operating system for embedded applications like this free RTES, which helps you to schedule different tasks and, for example, implement a control system or implement an Internet of Things application, which, for example, will be some sensors you have in the field to measure temperature, humidity, or so on, or even to control some pumps, some fans, and so on, right? So we have all these devices, the application you would write in software, as Alex has told you. And now the big idea is how does it then really the hardware look like where you run this application on? And this is a field I have been working in for quite some time, so I'm coming more from the design methods direction, where we're looking into what kind of tools do we need to build these systems, but also I have done a lot of work, for example, into modeling these embedded systems, especially the hardware. Okay, good. So what would be covering in about 2 days will be, you have seen how to program in C. And what you also have seen is that the compiler will take the C code and he will emit assembly code for your target processor. So we'll have a look into how does this assembly code look like. And we will look into some special assembly code, which is the so-called RISC-V, for the so-called RISC-V processor. And the RISC-V processor is a very interesting so-called instruction set architecture because it's open and it's also now becoming really a hot topic in the embedded domain, but also in other domains. Okay, and then if we know from C how do we get this assembly, then we also have to see how is this code executed on the actual processor. And there we will look into two architectures. One is a single cycle architecture where we have a processor which takes one cycle to execute one instruction. But this is usually not the way that you would implement this in hardware. But in hardware, usually what you're trying to do is you're trying to build up so-called pipelines. So we will also look how could you take this processor, separate it into different stages, and then put these stages together such that they work in a pipeline fashion. And if we know this with that, then we can also go and look a little bit what is the execution time we have on these embedded processors. And if we look into the execution time, we also have to look into, for example, what is the effect from caches, which are usually used to cache some data near to the processor. And then if we have this hardware, we know how the hardware, how the program is executed on this processor hardware. It's also interesting how can you connect this processor hardware with other modules on your embedded processor and an embedded chip like a microcontroller. And for that, we will also have a short look into how do the on-chip buses work and what architectures do we find there. And then if we can connect another module, we also have to look, what is the interface from the software running on the processor to some other hardware modules you have on your chip. And this is the so-called hardware-software interface. Okay, so I'm very much looking forward to cover all these topics with you. And hopefully that will be very interesting for you. And then we will now go through topic by topic. So now let's have a look into the RISC-V instruction set architecture. So what is an instruction set architecture? So an instruction set architecture describes several components of the behavior of a processor. So the first thing it describes are what is the state of the processor, which usually means what registers a certain processor is having. Then the next thing, of course, which is a very important part, is what instructions does the processor understand and execute. And this would be, first of all, how are they encoded in machine code, and then also how does the assembly code of these instructions look like and what is their behavior. Next to the behavior of the instructions, you also have to specify some additional behavior. For example, how does the processor react on exceptions? So for example, what's happening if you have a division by 0? How is that indicated to you? What's happening if you have an overflow? What's happening if you access some memory region which is not legal? Right? And this is also specified. And what's happening is, why would you define such an ISA? So the ISA basically is the interface between your compiler and your hardware. So if you run some program in C and you want to execute on a specific processor, the compiler has to know how does the instruction look like and then generates the instructions for that processor. On the other side, the guy who is designing the processor itself, the hardware, he has to know what kind of instructions this processor should be able to execute, what internal state it has to keep, so that the ISA really is the kind of interface between the software and the hardware. And you could say it like this, right? So if you see down there, you know, the instructions are a little bit like the words of the processor language, and the instruction set architecture then is the vocabulary of that processor. Okay, now let's take an example just to give you an idea what is actually assembly code. So assembly code is separated into different instructions. We have here one simple example where we say, okay, this is an instruction which has this keyword add, which means it's an addition. And then you have to say on what state of the processor should this addition be done. And here we have basically 3 such IDs for different states, registers of the processor, x1, x2, and x3. And then basically the ISA also defines that the first one is your destination register where the result should be going, and 2 and 3 are the operand registers. So the behavior would be, if you execute this instruction, you would read over this rex keyword, means you read the value which is in register x2, you read the value which is in register x3, you sum them up, and then you write them back to the register x1. All right, so in order to be able to define such a behavior, we have to know what are the states we can modify. So these are the registers, right, of the processor. This one we have to define in the ISA. We have to define what are the IDs, so how can we address these different states. So in this case, x1, x2, x3. We have to access the values, right? So we have to know they are in this register file located. And then we have to know that for an addition, we have to use this add keyword, and that the first parameter is the destination, the other 2s are the operands. Right? And so all these things, right, in order to specify this instruction, all this you find in your so-called architectural reference manual, which is a description of the ISA of your processor. Okay, so now where do you see this assembly code? So usually, right, what you have learned so far is, and what you know is how to write C code, right? So you would write something like A equals A plus 4. You would give this to your C compiler, right? And the C compiler actually emits then instructions to your target processor, right? So if your target processor is a RISC-V processor, then it would look like this. You would say add I, and then A might be stored in register x10, so we would say add 4 to the register x10, right? And but sometimes, and this is also often done in embedded, you might even write yourself this assembly code. So if you have some very critical code you want to highly optimize, then you could even write it in assembly, and you can mix it with some C code even. But the thing is, these compilers are already very good. They do a lot of optimization. So you have to be a very experienced assembly code programmer actually to write code which is better than what your compiler will be getting you. So usually you can actually move to C and you will get quite some very good code there. And then the assembler, he takes this assembly code either directly or from the compiler, and he then generates your machine code, right? So the machine code then would really be This is a hex word, right? So it's a binary, 32-bit in this case, 32-bit digital value, binary value, and this is the value you would find in your memory on your processor, which is loaded by the processor, and then the processor would know this binary value actually represents this instruction. Okay, good. So now let's have a closer look into this assembly code and the ISA. So first of all, you have to, there are different terms used for processors. We now learned what an instruction set architecture is, right? We will later also look what is the microarchitecture. So that is, there might be different processors which understand the same ISA, and they might have a different structure internally. So they might be a single cycle processor, there might be a pipeline processor with 3 stages, there might be a pipeline processor with 5 stages. And this is then called the microarchitecture. So there could be different microarchitectures, but they're executing the same ISA. And then, if you have such a microarchitecture, you want to bring it on your chip. So let's say you are producing a microcontroller, right? So, or ST. ST is producing a microcontroller, ST32, something microcontroller, and they will put a certain microarchitecture, so processor on it, for example, from ARM or another vendor. And then you will fabricate this chip, maybe in a 90 nanometer technology, and this is then called one implementation. Right? And this implementation is this microarchitecture and supports this ISA. One of the big IP vendors for processors is ARM, so it's quite famous. And they use a little bit different terminology. So they call ISA architecture revision, and a microarchitecture is already called an implementation for ARM. Right, so be a little bit careful, so especially the terminology as it's used in ARM documents, which you might encounter if you go into the embedded domain later professionally. The terminology is not what you usually find in the textbooks. Okay, now why did I choose the RISC-V instruction set? So as I said, for example, ARM is a big vendor of processor IP. They're not selling chips directly, so they're not a semiconductor company, they're really an IP company, but a lot of semiconductor vendors are using the IP from ARM. So for example, NXP, TI, Qualcomm, and so on, right, are using ARM. And if you look, for example, into your mobile phone here, right, you would actually have here a lot of ARM cores on it, right? So for example, these Snapdragons processors are actually ARM-based processors. And these ARM processors go from very, very tiny microcontrollers you might have in your washing machine or in your coffee machine up to these very powerful processors you have now on your phones or even on your tablets, or even there are now some laptops and so on running on ARM. There's even now a supercomputer, right, which is running with ARM processors. Okay, but the problem a little bit of ARM is, of course, it's kind of a closed ecosystem. So if you want to use it, of course, professionally, you have to pay for ARM. And also in academia, it was hard because you're actually not really allowed to build ARM processors on your own, right? You have to buy them from ARM. So actually what the people at UC Berkeley, University of California in Berkeley, they said, okay, let's also have another instruction set architecture which is free to use. And they invented this RISC-V as really an open ISA, which can be easily used in academia. You can just buy processors, build processors with it. And, but it's not restricted to academia. So you're also, of course, used or able to use it industrially, commercially, and it's really free to use, right? And therefore, now it actually also became quite a hot topic for industry to adopt it. So now it's, you can say, in some application fields, also industry is looking into, can we use this RISC-V ISA instead of maybe other commercial ISAs? And therefore, I think it's quite interesting to have a look into it. And also, it was kind of designed very recently, so it's one of the most modern ISAs which are out there. So let's have a closer look into this register, or this ISA from RISC-V. So let's start. So RISC-V has, the state has 32 registers. And you can configure how wide these registers are. So we will now also just take the standard case saying each register has 32-bit width. And if you're looking into how to address these registers, into the naming, you will actually find two IDs. So one ID is just a normal name, which is X, and a number, which goes from 0 to 31. So you can just say it's X20, X21. But then, if you have certain programs, some registers have different roles. And in order to indicate what is the role of the register, you have these so-called ABI names. So for example, the register X0, this is kind of hardwired to 0. So we'll always have the 0 value in that one. And therefore, the ABI name is 0. The register X1, for example, this is the RA register, right? And this has a name because it has the return address. So if you're calling a function and this function wants to return from where it was called, it finds this address in RA. Okay, another one is the stack pointer. So this is also important. So if you want to save something on the stack pointer tells you at which location you are at the moment in the stack. And so on and so on. And then there are some registers you can use just for computation. And you can basically say there are three classes. There's the T registers, there are the S registers, and there are the A registers. So the T registers are so-called temporary. So we'll use them for temporary local variables. And the A registers, here, for example, you find the function arguments, right? So the first function argument is an A0, the next one is an A1, the next one is an A2, and so on. And also what's happening is in A0, you also have the return value. So if you want to return, you put the value into A0. So these are also the ones you can use in your function. The S ones, and this is also indicated by this here callee, and we'll later look into this, there you have to be a little bit careful when you're using them. And this has to do with also this ABI. So what is this ABI? So the ABI is the so-called application binary interface. And it basically specifies how you should write assembly code. And the idea is that especially if you mix assembly code with code that the compiler is using, then of course if the compiler generates some code and he wants to call a function that you have written in assembly, he has to know what is this interface to this function. And this is basically specified in the ABI. Right, in the ABI we have these assignments of the registers. We also have these roles saying you find the function arguments there and so on, right? And also it tells you who is responsible for saving a certain register. They are so-called callee saved registers, and these ones you have to be careful. So if you specify foo2 and it gets called by foo1, then you are not allowed to change these registers in foo2. If you want to change them, you have to make sure before you return, you restore the value. For example, you can take the value, put it on the stack, and restore it later on. But you have to be careful. And these are these S registers. And then there are these caller saved registers. So these caller saved registers, foo2 can use, right? So foo1 has to make sure before it calls foo2 that it basically stores all the values in this register before it calls it. Otherwise, it will not work. Or otherwise, foo1 will lose this value, right? Because foo2 can modify it. Okay, great. So then we basically have specified how this ABI is working. Now we can go and look into the instructions. So the instructions, they are basically in the encoding, right? There are 4 types. The instructions also have, for this instructions that RV32 has 32-bit wide instructions. And now we are looking how does this machine code look like. And there are different formats for this machine code. This is called R-type, I-type, S-type, and U-type. R-type is, for example, for register. ALU instructions, right? And this is, for example, like this add instruction we have seen. So this opcode would tell you this is an add instruction. Here in this field, in the bits would tell you what is the destination register. And then these bits will tell you what is the operand register and what is the other operand register. All right? Now, in order to understand what a processor is doing, we don't have to go down to this machine code and look into the hex numbers or binary numbers. For us, it's basically enough to see what is the assembly code, and how this assembly code gets executed on the processor. All right, then how this really looks like, this is really up to the assembler to generate and later to the processor decoder to decode. Okay, now let's just get kind of a list of instructions. We will not look into all instructions in the RISC-V instruction set, but we will just look into a few instructions we can use to get a better understanding how the assembly code looks like, and also get an understanding later on how we can execute this on a processor. So the nice thing about the RISC-V ISA is also it's kind of structured into subgroups of instructions, and we will look into two of these subgroups. So one is called the RV32I, so this is for integer instructions. So these are basically the basic instructions you always need, right? So this is register, register, integer, register intermediate instructions. So this is when you have some constant value, you want to put it there. How these constants are really encoded in the binary code, this is usually very strange, so we won't have a look into it, but you have to be careful. And then we need some control transfer instructions like jumps and branches, right? And then also we need some load and store instructions. Because what's happening is RISC-V is a so-called load store architecture. So if you want to, for example, interact with memory or change a memory element, you first have to load it, then you have to do the operation, and then you have to restore it back. So if you have, for example, an array and you want to sort two elements of the array, you first have to load both elements, then you have to compare them, then you might have to switch them, and then you're storing them back into the array, into the memory. And additionally, so with that you can already build a processor, right, which can do these integer operations, but then you might want to have a little bit more complex processor. Then you can say your processor also should be supporting multiplications in integer, so you would have an integer multiplication in the division instruction, and this is then called R432M, right? But this is still integer, right? You can then also come up with a new, more complex processor, which, for example, also supports floating point. And this would then be another subset of the instructions. But we will not go so far, so this is sufficient for us. Okay, so let's just go through the list of instructions so you get an idea what kind of instructions you find in there, how they are behaving, and then we're actually able to already translate C code into assembly code and see how that would execute on a processor. So if you have these integer, register, register instructions, we first have the name of the instruction, then we have always destination, operand 1, operand 2, right? And then we have destination register is set to operand 1, operation, operand 2. So what you already seen is the addition, right? Now I'm using here the API name in the example. I'm not using the normal register name with the X, right? So I'm using the API name A1, A2, A3, and the behavior would be register A1, the value is changed to be the value you have stored in A2 and in A3, and we sum it up. Then subtraction, very easy, right? You're just subtracting the two values. Then there are two compare instructions. That means you give the two operands, and what's happening is if A2 is smaller than A3, then it will set a 1, which means it's true, into A1, or otherwise you will set a 0 into A1, meaning it's false. Right? There we have a comparison. And there's also, you have to be careful, always whether a register keeps a signed or unsigned value, right? So is the most significant bit a signed bit, or is it still part of your value? So, so you have to say, for example, do you have an integer or unsigned integer in this register, right? And therefore, there's a second instruction. So if you have unsigned ones, then you have to make an unsigned compare. So this is indicated by this U. And you'll find this everywhere. You always have the version for signed values, and you have a second version for unsigned values. Okay, then we have, of course, all the usual logical instructions, right? So you make logical operation at A2, A3 with AND, or the XOR, right? And this is done bitwise, right? Per bit you make an AND, per bit you make an or per bit you make an XOR. We can also shift, so we can shift left. So we're going into this direction. So what you're doing is you're shifting A2 by as many elements as you have specified in A3. So if A3 is 2, we would shift A2 by 4 elements. And what you do is from this side, also from the right, you're shifting zeros into the register, right? So for example, if you're shifting a value by 2, just because it's a binary value, right, would mean you're actually multiplying by 4, right, the value. You can also shift right, right? If you're shifting right, then you're filling in zeros from the left. And this would then be, for example, if you shift it by 2, so if A3 is 2, then you shift the value of the A2 by 2, that would be division by 4, right? And if you make a shift right arithmetic, then you're looking whether you have most significant bit is 1 or 0, right? So the idea is if you have a signed value, you would shift ones in, and if you have if the most significant bit is 0, you're shifting zeros in. And that would mean even for signed values, you're not changing the sign bit, right, while you're shifting. And therefore, it's called arithmetic, not logic. Okay, so with that, we already have quite a lot of instructions we can use. Now what we can do, and this is this integer register immediate instructions, we are basically going and taking a constant value. So for example, instead of doing add with 2 registers, now the second operand is a constant, which means we're taking a certain register and we're adding a constant to it and we're storing it back. Right, and there's basically to most instruction we already have seen, there's also an immediate version, right? So you can shift I with an immediate value, unsigned, and so on, right? What you have to be careful, there is no sub I, right? There is no subtraction with a constant. What you're just doing is you're taking the add I and you're just taking a negative value, right? And this gives you like sub A1, A2, 3 is the same as add I, I1, A2 minus 3. Also, there's one operation, especially if it's a NOP operation. You can put this in, it actually does nothing. And then we also have a so-called move operation, where you just copy the value of A2 into A1, right? And this is a so-called pseudo instruction, which means actually it's just to simplify the coding, but what's actually happening in the processor, it's just using the add I instruction, and it's having A1, A2, and then it's just 0. So A1 equals A2 plus 0, which means A1 equals A2. Right? So we don't need another encoding for the move instruction. We can realize it with one instruction we're already having, and therefore it's called a pseudo instruction. But if you're writing assembly code, the assembler understands this instruction. Okay, now we have to be a little bit careful. Now we also want to be able to do transfer of control. And there we have to be a little bit careful and think of what are these instructions actually doing. So what they are doing is they are changing the so-called program counter. And the program counter tells you which is the address of the next instructions to execute. So for example, you can have here in your memory, you have your program that the processor should execute, and then you have like instruction 1 you want to execute, and you have instruction 2 you want to execute. And they are apart 4, right? The address goes up from 0 to 4. Why does it go up from 0 to 4? Because the address is per byte. And if you have instructions which have 32-bit, then this is 1 byte is 8-bit. Therefore, each instruction has 4 bytes. This one means this one is addressing the first instruction, and then 4 bytes later comes the next instruction, and then at x8 comes the next instruction, right? So for example, if you don't want to execute this instruction, you can take the PC if it's to 0. If you add 8 to the PC, it will just jump over this instruction, right? And this is then kind of a transfer of control. So we have 32-bit instructions of 4 bytes, right? So the addresses are always, or each instructions are part 4 byte. And if you're reading a certain element, right? So if you want to get an instruction, we use this mem operator, and this gives us the memory element for this address. So we have some instruction memory, we give the PC as an address, and what we're getting back is the value stored in the memory at this address, and this is actually our instruction in machine code we should execute. And as I said, these control transfer instructions, they are basically modifying this PC. So normally for all other instructions, the PC always increments by 4. So you would execute instruction 1 plus 4, instruction 2 plus 4, instruction 3. And then if you want to do some jumps or branches or function calls, which then implements loops, if-elses, and so on, or function returns or function calls, then you do something different. You don't do PC plus 4, but you jump to some other location in the program. Okay, so what kind of instructions do we find here? So we first find the unconditional jump. There we have the jump and some offset we want to jump to. So the behavior would be, we have the PC. For the other instruction, it would always be PC plus 4. Here it's offset, but the offset gets shifted to the left by 1. So you take the offset actually times 2. This is what the shift is doing, right? So if you specify J8, which means you should jump 8 ahead, which would mean you're jumping over the next instruction, right? This would you would first indicate, but actually if you look into it, this 8 gets also shifted by 1, so it gets multiplied by 2, so you basically have PC plus 16, so we are jumping over 3 instructions to the 4th instruction, right? So the next 3 instructions would not execute because the PC just jumps over them. If you're writing assembly code, usually you don't have to compute what this offset is. You rather put in some symbols into your code, and then you can just say, I want to jump to the symbol, and the assembler will find out what is the offset to get there. Now if you make a function call, right, you're calling some function, you take the PC to where the function starts. Then at some point, of course, the function finished, and you want to return to the function which was the caller, right, to the original location to continue the execution. And therefore, you have to save the return address. And this is what you do if you have this jump and link instruction. If you have this jump and link instruction, it does this same behavior as the jump, but it takes also PC plus 4, which is the next instruction to execute, and it puts it into the return address. So the jump and link instruction also saves the return address. And then also you have to jump to a register. So for example, if you're at the end of the function, then you have to say, now I have to go to the return address, and then you can take the jump instruction and put the register there. And this will bring you to this one. But even though I think this is not correct, I think this is actually, the code is JR. Pretty sure about this. I have to check it, but I think it is JR for jump register. And this is for the function return. And in order to make it a little bit simpler, you don't have to write this jump to register RA. There is also a pseudo instruction which is called ret, and this means you want to return from the function. Okay, so we have the jumps. So now what else do we need? We need so-called branches. And branches basically means you have a condition. Only when you have a condition, you do the jump. So for example, there would be one example where you have a branch, but only if it's equal. You put 2 registers, and then you put the symbol you want to jump to, right? So if A1 and A2 are equal, then you would jump to the symbol, loop start, else you would do nothing, right? And for example, this would be if you have a while loop, you would check, do you still have to execute the while loop, or are you finished, right? And you have this equal, then you have not equal, you have lesser than, unsigned lesser than, greater or equal than, and then unsigned greater or equal than. These are kind of the conditions you can put after the branch in order to make sure that you have the right one. Okay, now we have these arithmetic operations, we have our branches. The only thing is, what is missing is we also want to interact with memory. And for this, we have our load and store instructions. They are responsible to interact with the memory, right? So memory could either be the data section, where you have your global variables, it could be the stack, or it could also be the heap if you're using a dynamic memory allocation. So The same thing as with the program counter, right? So you take an address and you want to have the memory stored, the memory element stored at this address, right? Now the load instruction would fetch you a certain value. This is actually very easy to what the PC is doing when it does an instruction fetch. You put a certain address, which could be, for example, 0xA00, right? And then it would return to you a data word, right? It would return to you the data word, which is stored at 0xA00. And the data word also has 4 bytes, right? So it's 32-bit. And so each data word is again 4-bit apart. And for the store instruction, it's a little bit different. So, right? So now you are actually not reading from the memory, you're writing to the memory. So you would need the write interface of the memory. Then you would give the address you want to store. You would give what data word this would be, and then this data word would be stored at this address. Right? This is what's happening in the data memory. And the instructions, right? One is load word. This is for loading a word. You give where you want to load to, so this is the result register. And then you are giving one register, which is the address, and you can also give an offset, right? So you would say, take, and this is why this has brackets, so A2 is an address, and you would say, take the value, so A2 is an address, take the value at this address, but add 80 to it, and then give me the value back. And since it's load word, it has 4 bytes. And the same is true for store word. For store word, what it does is it takes the value given a register, so this is also an operand now, and it stores it at the address you have given here, so A2 plus 80. And there are also other instructions if you want to just to store a byte or 2 bytes, right? Which we will not look into, but there's also store byte or store so-called half word. Half word means 2 bytes, half of a word. Okay, great. So this is the complete integer instruction set. If you want to do multiplication, then again we have signed and unsigned. The issue about the multiplication is if you're multiplying two 32-bit values, then the result can actually be as wide as 64-bit. Right? In order to not lose anything, you have 2 multiplication instructions. One is the mul instruction, which multiplies RS1 and RS2, and it stores it into the destination register, but these are the lower 32-bit of the result. So if you know that RS1 and RS2 are very small values, and you know the result cannot be higher than 32-bit, this instruction is enough. If you want to sure you also get the upper 32-bit, you have to rerun the whole thing, but use the mul h, and this mul h will give you the higher 32-bit. So for example, if you take both of these instructions, you apply them on the same registers, this is the lower part, this is the higher part, then you would get the complete 64-bit of multiplication result in these 2 32-bit registers. So, and the same, you have the same instruction for multiplying 2 unsigned values, or then you have even the same instruction if you want to take 1 unsigned value and 1 signed value and you want to multiply them. There's also an instruction for this. Division is the same thing, right? There's a division instruction where you give it 2 registers and then it will divide it and put the results somewhere. So this is integer, right? So you only get the integer value. So if you also want to get the remainder, there's an instruction to also give you the remainder of the division, right? Which is basically doing a modulo operation. And we also have variants again for unsigned and for signed unsigned execution. Okay, so this, now we are having a whole list of instructions we can use. And with that we can actually do real programming the same way as we have in C. And we can compare how does C behave versus assembly code. Okay, so now that we know the instructions that our RISC-V processor can execute, we can now take these instructions and we can try to write complete programs using these instructions, and that is basically what you do when you do assembly level programming. Right? So you can do either C level programming, then the compiler will generate the assembly code for you, or you can go on and do the assembly programming on your own. And this makes sense either when there is no compiler for your system, or if it's a very critical function and you think that whatever the compiler is giving you is not optimized enough, then you can do and try to find a hand-optimized version. Okay, so let's have a look what kind of rules there are for the assembling programming. So we have looked into this already. So this is basically what we found and is defined in this ABI, so in the application binary interface. Right, so the first thing you have to do is when you're starting some function, for example, the function foo1, you're starting it with the label, right? This is the symbol, right? So that other functions who want to call foo1, they would do a jump and link to this symbol. And then we know that in these registers, which have an ABI name starting with A, there we find the function parameters, right? So we find the first one in A0, the second one in A1, and so on, right? And if you have a return value, so if you want to return a value, then you have to move this value to A0 before you go and do the function return. So that the function which called your function knows, aha, now I want to take the return value and I find this in the register A0. And finally, for returning from your function, you take this ret instruction for return, which basically is jump register return address, right, if we've seen before. Now, of course, you might not do only operations on the parameters. You might also want to define some local variables. And for those, you actually want to use these registers starting with T. So all the registers starting with T, that is the typically kind of a coding style is what you would use for the temporary variables. Okay, so let's get started and let's try to write a few assembly programs just to get an idea how this works. So let's take a first C code example. So this is our C code function, right? So what it does is it computes the absolute value from your parameter you're putting in. So it have one parameter which is integer, which you put in, and it's returning one integer value, right? And what it does is if a is smaller than 0, it basically multiplies it with -1, and this you can also express as that you take 0 minus a, right? So if you give it -5, it will return 5 to you. This is the absolute value. If you give it 5, it will just return 5 because it's already positive, right? So it just does, if it has a negative value, it changes it to the positive value, right? This is what you want to do, right? And this is your C code. This is nicely doing that. And how does now the assembly code like? We can go through line by line, right? What we already seen is the ABI tells us A is in register A0 when we start the function, right? So we know where to find A. A we are finding in A0. And the return value we should also return in A0, right? So what we can do is we put the symbol name, right? This is the symbol. This is our function start. So other functions, as I said, can jump to this function. Then we have to find out if a is greater than 0 and if smaller than 0. So if a is smaller than 0, we want to do this operation. So we can turn this around and can say when a is larger or equal to 0, we don't want to do anything, right? Only when it's smaller. So what we say, if it's greater or equal than 0, right, then we would just kind of return. There's nothing to be done, all right? So what we're saying is if it's greater or equal than 0, so if A0, which holds A, is greater than equal to 0, we just right away jump to the return value. If this jump is not done, right, then it just goes to the next instruction. The next instruction is actually what is you see here, right? So what we're doing is we're taking sub A0, 0 A0 means A0 is now 0 minus A0, right? And this actually implements right A equals 0 minus A. And then it goes to the next instruction and returns, right? So if this is true, so if it's greater or equal to 0, it will just return, because then you already have a positive value, nothing you can do. It's already in A0. And if it's actually smaller than 0, you would run also this instruction, and then it would change the value from a negative value to a positive value. All right? And as I said, this return instruction actually is a pseudo instruction. So what the processor is really executing is jump register to the return address, right? Because that is where the program which called you, where it was located. Or the next instruction after the function call, from where you came from. Okay, I hope this became clear. Now let's take a more complex example. All right, so this one calculates the greatest common divisor between two values, right? So you give it A and B, and it will return the greatest common divisor, right? So if you take, let's say, what can you take? If you take 18 and 36, right? The common greatest divisor should be 9, and then you're returning 9 to it. Hopefully, I think this should be correct. Okay, and now let's see how we can write the same thing which we have here in C code in assembly code. So the same thing, you're starting with the symbol, which is the function name, so you can jump to the function. Then, basically, the while loop is running as long as A is non equals to 0, right? We again turn this around. So we're saying if A is equals to 0, then we want to leave the loop, right? So we jump to GCD done, which is after the loop. So we are saying, okay, if A is equals to 0, we want to leave the while loop. Therefore, we are jumping out of the while loop here. So this is basically implementing your while loop. Then the next thing is we have an if statement, an if-else statement. So we first have to see, okay, what is the condition? The condition is A greater or equals than B, right? And again, what we are doing is we are turning this around. So we are saying, is A smaller than B? So we have lower than, LT is for lower than. We have A0, right? So A0 has the first parameter, and we know the first parameter of the function is A. So we have A and A0. Then we have A1. A1 is actually equals to B, right? Because the next parameter of the function is in B, is B, and this is an A1, this is the second parameter. So if we turn this around, so if A is smaller than B, then we want to execute the else branch, so we are jumping to the else branch. If we're not taking the else branch, we are actually in the if branch, right? So we continue with our if branch. So we have to say what's happening in the if branch. So in the if branch, we make A equals A minus B. Very easy. Sub A0, A0, A1, right? This is A minus B, right? This is due to the mapping to the registers. So here we have A equals A minus B. And then actually, if you go on, right, here you have the else branch. And actually what's happening is you're jumping back to the head of the while loop. Therefore, we are just jumping back to the head of the while loop. And since the while loop is the first thing you have in the function, you can just jump back to the function start, which actually is also the head of your while loop, right? Otherwise, if there would be some setup before the while loop, you also would have to have a GCD loop symbol somewhere, right? But here we don't need that. Okay, and now we just have to also do the else, right? And if you go to the else, we have all these kind of copy statements. So T should be equals to A. Now what is T? T is a local variable, right? So it's a temporary local variable you just need for the function. If you think about the first slide we have seen, these local variables, we should use a T register for it, right? So we can say, okay, let's use the T0 register for it. All right, so what do we have to do? We have to say T equals to A, so T0, this is mapped to T. A0 is A, so we copy it over with the move instruction, right? This just moves the value from one register to the other register. Then B should be A, right? So you take the B value, you move it to A. Here, this is the register A1 for B, the register A0 for A. Then we have to say B equals T, same thing, right? This is the B register, A1, this is the T register, T0, and you did it, right? And then again, after the else, we make the next iteration of our while loop, so we jump back to this head. And here we are checking whether we are still continuing with the loop or if we should kind of move out of the loop. Now, if you're moving out of the loop, you have to be careful, right? So here, after the while loop, you're now moving out of the loop. You want to return B. B you have mapped into register A1. And due to the ABI, the return value should be in the register A0. Right? Therefore, we have to move the value. So A1 has the actual value of B. And for returning, we have to move it to A0 because this is where the return value should be located. And then we can do our function return. And this function here and this function here are doing exactly the same thing. So you can either call GCD as you do here, right, from any parts of your program, or you can have an assembly part of your project, and you can call it GCD also from C code if you like to, and it will actually do the same thing, right? So this works. Now let's take it even a step higher. So let's try one more level of difficulty, and let's see what's happening. Now we take another function, and this function basically takes as input pointers, also arrays. So if you take this one, it's basically A is a pointer, and A points to an array which has 4 elements of the type integer. And the same is for B, and the same is for C. And now what you want to do is, you're iterating over these 4 elements, with I, from I going from 0 to 3, right? 0, 1, 2, 3, 4 elements, and you're always adding the element of A and the element of B, and you're copying this into the array C. So if A, B, and C should be arrays, right, or vectors, so maybe you do some, have some vector with 4 elements. C is basically just a vector sum of A and B. You give it two vectors with 4 elements, and it will actually, what it will do is it gives you back the sum. All right, and now the difficulty is you have to think a little bit differently. If you have these vectors, the important thing you have to think about is these are now pointers to memory locations. And what you're doing is these 4 elements are always in memory. You're just bringing them into the registers, do some operations on them, and then you are storing them back into memory, right? So what's happening is, as you can also see, this function is void, so it does not return anything. So why is it not returning anything? Because it just modifies the elements of C, and you will find C back in memory, right, later on. So you have to give him which location is C located in. So this is actually what you find here. So this is a reference where C is located in memory, right, your array. And yeah, this is an important thing. So registers, if you move a registers, they can either be values or they can actually point to location into memory. And if you look into the assembly code, we see this. But this is not so, it's a little bit more difficult to think about it. But that's exactly how the machine or how your processor is dealing with these arrays and pointers. Okay, so let's get started, right? So as we are saying, the parameters are in the registers A0, A1, and A2. But you don't find any values there. These are the base addresses of your arrays. So they're pointing basically to your first element in your array, so to A0, B0, C, element 0. Then we have one local variable, right? We have I, and this I, we are already, as we said, we always want to use a T register for this temporary, so we use T0. Now we have another constant 4 here, and this 4 we put into also a temporary register, which is T3. Okay? Now let's get started. So we are, again, we take a symbol, right? This is just a function name. Then we have to initialize our temporary variable. So I gets initialized to 0. Now you cannot just move T0, 0. This doesn't work. So the move instruction always copies from one registers to the other one, right? So, so you cannot say like move T0, 0. You could say move T0 taking the 0 register. This works, right? But basically what's happening in the processor is this would just be a pseudo instruction. Basically what you're saying is T0 is register which has always value 0 plus 0. Right? This is what's happening in the processor, and then you get 0. The same is for this constant 4. You're saying the constant 4 is basically take 0 and add 4 to it. And then you have 4 in the register. Okay, then we are starting our for loop, right? So the for loop now gets another label because we don't want to do this inside the loop, right? We only want, this is basically set it up before the loop starts. So we only want to do in the for loop these types of instructions, right? So we put another symbol here to indicate here the for loop starts. Now what we have to do is we have to load the element, right? We have to load the element from the vectors to add. So what we're doing is we are again taking temporary variables, so T1, T2 are temporary variables, and now A0 is an address, and we're saying give us the value at this address. So in the first time when you're starting the loop, this would point to the 0 element of the array, and now you have the 0 element of the array, so A from 0. You move this into one register. And the same you do for B. You take B, you move that into a register. So, right, you take the element stored at the location B. Right, this is the important thing. Put it in the register. Then you do the add operation. So you do T1 and T2 hold these two values, right? So you're adding T1 and T2. And you get the result, and now you don't need T1 anymore, so you can just overwrite it. We don't need to take a new register. And then you're taking this value, which is the sum of these two, and you're storing it back into memory, and at which location in memory. This is what indicated by C, so where the pointer C points to, right? So A points to a location, B points to location, C points to location. We're loading from A, we're loading from B, and then we are storing back into the location indicated by C. Now what's happening? Now if we do the next iteration, right? So we started with A0. In the next iteration we want to have A from 1. Now in order to get the pointer to point to A of 1, we actually have to increase the pointer by 4. So why now by 4? Because we set each in the memory the addresses addressing bytes, right? So if you have an address plus M1 is the next byte. So now since A, B, and C are integer arrays, and integers are stored as 32-bit values, each integer value occupies 4 bytes. Therefore, what you have to do is you have increased the address by 4 to get the next 4 bytes, which is the next integer value. All right, so you're just taking all the 3 pointers for A, B, and C, and for each pointer, you're just adding 4 to it, and now they are basically pointing to the next element. Then we have also to do the I. We have to increase the increment of I, right? So we have to increase I by 1, and then we have to say, okay. So I, now you have to be careful. I is unsigned, right? So we have to do unsigned, and we want to check if I is smaller than 4, right? So we have to say lesser than. Unsigned, and then we take T0, which keeps I, right? We have T3, which is keeping 4, and if this is the case, we are basically jumping back and say, okay, we're not finished yet. We have to jump back to the beginning of the loop, right? And if I then becomes 4, this is not true, and then we can just return. And we don't have to put anything into A0 because this is a void function, so there is no return value required. Okay, so I hope this kind of gave you an idea how you can write programs into assembly code. And this is now very helpful because when we now know what these instructions should be doing, we can go on and look into how should the processors look like which are executing these instructions. Okay, so now let's have a look into how is an embedded processor built up, so typical so-called RISC processor. how does it execute the instructions, and how it is implemented. And here we will first look in the simple implementation, which is a so-called single cycle implementation. Now we have already seen a little bit that we are looking into RISC processors. So what is really a RISC processor? So if we try to classify processors, we have these kind of RISC type processors, and kind of the idea of them is they have a lot of registers. They have usually very simple instructions, so-called 3 address instructions, which have 2 operand registers, for example, and 1 destination register. So you have 3 addresses you are actually changing. They have very so-called simple addressing modes, so there are only simple ways you can load and store from memory. And usually the ISA is thought to be very simple. And typical examples are, for example, MIPS, PowerPC, ARM is a typical RISC instruction set. ARM actually stands for Advanced RISC Machine, that's the acronym. And of course, new now also RISC-V is a RISC instruction set. On the other side, you have so-called complex instruction set computers, which are the CISC machines. They have fewer registers. They usually have only 2 address instructions, but they have kind of a wide variety of addressing modes where you can also modify data in memory. They have very different classes of registers and a very different length of instructions. And of course, one typical example, therefore, is x86, which is a CISC instruction set. RISC is actually more used in the embedded domain because it's easier to build low-power processors using RISC machines. So for example, if you consider that also Intel was trying to take their Atom processors and put them into the mobile phones, they actually had a very hard time, since this was a CISC instruction set, to really bring it to low power. Why, for example, these ARM Snapdragon processors, they are RISC machines, right, which are now widely used in the mobile phones. And there it's a little bit easier to bring them low power. And these RISC machines can actually become very, very small. So even these very small microcontrollers you might have in your washing machine and so on, they are usually some ARM chips which are very reduced in their instruction set and therefore can be nicely used in these low power microcontrollers. And of course, RISC-V tries to give you the same advantages that, for example, you have when using the ARM ISA. There are also other designs, so it doesn't only have to be CISC or RISC. So for example, one typical other design would be kind of a stack-based processor, where you actually do the operation not in registers, but on the stack. But this is kind of very specialized processors you would only use if you have a certain application where this makes sense. Okay, the other classification we're doing, so we are only looking into so-called general purpose computers, right? So these are processors where you can write different C programs and they try to kind of support a wide variety of applications and workloads and execute them in a nice way. So sensor readouts, sensor processing, control application, everything like this. Now, in the embedded domain, sometimes you have the processor should do a very specialized role. So for example, it should just do signal processing, right? And then you can go and put in a so-called application-specific instruction set processor, ASIP. And these processors, their instruction set is then very specific for the workload they are running. And one typical ASIP are these digital signal processors you can, for example, use to do audio encoding, decoding, or to do some video encoding, decoding, and so on. And they are basically, their instructions are catered for this workload, but they will not be able to support some other workloads. Right? But since it is embedded, sometimes you have a very specialized role for a certain programmable processor, you want to also consider these architectures. But here, the RISC-V instruction set, basically, this is for a general purpose computer. So this is what we're looking into. Then if you go more into the architecture, the microarchitecture, there are kind of 2 classes. You can either have a von Neumann or a Harvard architecture. Where for the von Neumann architecture, basically, there's one bus interface where you're loading instructions and data from and writing data from, while if you go for the Harvard architecture, the processor actually has two memory interfaces, and it can load over the instruction interface the instructions, and independently he can read and write data to the data memory using the data bus interface. And we will later see what kind of differences this does in terms of timing. Okay, so now I got an idea kind of how you can broadly classify different processors. Let's go a little bit more into detail. So we can have a Harvard or for Neumann, and then the idea is how do they execute the instructions. And there, for example, there are kind of, again, broadly three classes. We can have a so-called single cycle processor, where you take one cycle to execute each instruction. But the thing is, the instruction behavior can be quite complex. It might take you very long, so these processors might run actually a very low frequency, because in each cycle time, you have to do everything the instruction is doing. Right? So for example, a multiplication can be very expensive. If you want to do a multiplication in one cycle, the cycle must be very long. Therefore, the frequency of the processor, 1 divided by the cycle time, becomes very large. In order to deal with that, you can build so-called multi-cycle processors, where you're saying, okay, maybe an addition you do in one cycle because this goes very fast, but a multiplication, you would also say, okay, multiplication takes 4 or 5 cycles. And then you basically have the result such that you can basically have a smaller cycle time, because now only the addition has to fit into your cycle, while the multiplication can use several cycles. And with that, you can then bring up the frequency of the processor. You can run it at higher frequency. And then, and this is actually usually the standard design is, there's a better way of doing it, and this is usually what's always happening if you're going for hardware is, if you have hardware, you're trying to build pipeline. So you're trying to pipeline your hardware. That means you split the instruction into several stages, and then when one instruction leaves a certain stage, the next one can go into the stage. Right? So you basically have this interleaved execution of instructions, and make very good use of each stage, because while one stage is occupied by one instruction, the other stages are occupied by other instructions. But this also causes some problems, because sometimes this causes so-called hazards, and this one we will be looking into more detail when we look into the pipeline. But usually the pipelines, the nice thing about it, they can run with very, very high frequencies. Okay, good. So this kind of gave you kind of a broad classification. Now it starts with the most simple, the single cycle processor. And this picture now is an architecture which supports the integer set of the RISC-V processor, not the multiplication, right? You don't find a multiplier there. And now let's go through it, and then we will go step by step and see what the instructions are doing. Okay, so the first thing is we have PC, which is a program counter, right? The program counter goes into the instruction memory, it's connected there, it gets back an instruction. Based on the instruction, you might want to access some registers, and then you're feeding the registers to the ALU, and the ALU is the arithmetic logic unit. So what the ALU is doing is it can do addition, subtraction, logical AND, or logical OR, shifts, and so on, right? So all these operations are done in the ALU. The ALU gives you some output. Then you have an access where you can either access and write to the data memory, or you're reading from the data memory. And finally, the result should go back into a register. There is some coloring here. So the coloring means if it's blue, that's where you have the PC going on, so starting with me actually. And if it's yellow, that's actually the address to the data memory. So if you access this one, it's the data memory. And so the blocks are either memories or they are units which do something, right? And these arrows, these would be data buses, right? Wires on your system. And these multiplexers, of course, what they are doing is they're either choosing this value or this value, and they're forwarding it. So they are multiplexers, hardware multiplexers, which are multiplexing between these two buses, right? So a multiplexer either can take this or this one and put it forward. Okay, so this is kind of a cross-grained thing, and I think it becomes clearer when we have a closer look into what the instructions are doing. So let's start with an addition. So we have an addition instruction, and we have A1, A2, A3. So the resulting behavior should be A1 equals A2 plus A3. Okay, so this instruction is at a certain PC value, right? So you're loading the PC where this instruction is stored, and here you get the result back. So this is the result. This was what's the machine word which encodes exactly this instruction. So what you get back here is basically the machine code which says this is an addition, and this is your destination register, these are your two operand registers. And this instruction then gets decoded here, and what it finds out is, okay, my two operand registers are A2 and A3, so I have to read from the register array, register file. This is also called A2 and A3. So I'm reading these two values, right? And what I also have to remember is the resulting of the addition I have to store back into A1. So I have to decode, okay, later this would be stored into A1. Now, since this is not a controlled transfer modification instruction, but it's just an ALU instruction, the PC is just, the next PC we're having is PC plus 4, right? So the next PC we should have is the next instruction, and this is 4 apart because, again, 4 bytes apart, right? And we are forwarding this PC plus 4. Now the next thing what's happening is we are taking these two values and we're moving it forward to our ALU, right? So it would use this bus here, and the multiplexer would select this bus and forward it to this one. It selects this bus here, the multiplier selects it, and it moves it to the ALU. So at the inputs of the ALU, I now have the value which was stored in register A2 and the value which was stored in register A3. And the next step, the ALU would do the addition, right? So it would know, okay, this is an addition. There's, of course, some control logic behind it, right? Because the instruction decode has somehow to forward to the ALU that this is now an addition. So this is left out in this picture. And you get the result back. And what do we do with the result? We want to write it back into the register A1, right? So we have to forward it, then take this backward path, right? And here, to this backward path, we are basically writing it into A1. And the same thing is here. So here we actually want to have, as I said, the next one should be PC plus 4. So we take this PC plus 4, we're forwarding it. Now we have PC plus 4 here. And in the next cycle, this PC plus 4 goes here. And then we're loading the next instruction, and the next cycle is starting, right? And we are executing the next instruction and decoding it. Okay, so this was for an arithmetic instruction. Let's take the next type, a load word. So what is happening in a load word? So now we want to load a word. We want to store the word in A1. And what address do we want to take? We want to take the address A2, but we have a constant offset of 8. So if A2 is, for example, an integer array x, then plus 8 would be, we are looking into the element x of 2, right? The third element. So x0, x1, x2, right? 8 offset, right? So this is integer. Okay, good. Now, how would the processor execute this instruction? So we start with the program counter. Again, we get, first thing is we have to fetch the instruction, right? This is called instruction fetch. So we have to get the element where the have to find out that this is now a load. So we're loading this from the instruction memory. We are decoding it, and now we are getting A2, right? So this means this is where the address is. We know we want to write to A1, so we have to keep this in mind. We have to write to A1, and we're also decoding that we have this 8 offset, right? So we have to basically forward this 8 also, right? And of course, PC just should be PC plus 4, right, to the next instruction. So we are moving now the result, or the value, which is an A2, to the ALU, to the one input, and we're moving the 8 over this path to the other input. So now this multiplexer is selecting this input. This multiplexer is selecting this input. And then the ALU will do an addition, and it will add this 8 to our 1. And now, as I said, the yellow one is the address at the data memory, right? So this should become the address where we are reading from. So we are putting this now to the data memory and say we want to read the value from this address because this is a load instruction. And then the memory will return us the value at this address. And we take the value, we forward it back, and we write this value into the register A1. So now if this load word, as I said, was we want to access the element of an array x of 2, now this element of this array would be in our register A1. We can do some operation on this element and then might store it back into the array or some other array, right? And for storing back, we have to take the store word instruction. Here what we are doing is, again, same thing, instruction fetch. We get the instruction, we decode it, and now what do we have, right? So we find out that we want to read from the address A2, right? But we also want to find out that we want to store the value which is in the register A1. Right, so both of them are operands, so we have to read A2, which is the address we want to store to, and we have to read the value in A1, which is the value we want to store. And again, there's an offset given, right? So there's an offset given here of 8. So we don't want to write directly to the address A2, but we want to have an offset of 8 to write to. Now we are forwarding this again to the ALU, right? So we are forwarding A2, the value which was in A2 to the ALU. We are forwarding this 8 to the ALU. Then the ALU does the addition, right? So the offset gets added to A2. And that's actually a small typo here. So this should be, the bracket must be here actually, right? And on the other side, we also want to get the value in A1 because this is the value we want to store. So we put the address to the data memory, and we put the value we want to store to the data memory, right? And then what's happening is basically nothing more, right? So the data memory would just take over this value and would write it into the memory. And again, PC plus 4, right? So this is again, load the next instruction. So PC has to be PC plus 4 for the next instruction. Okay, and now comes the most complex instruction. And this is instruction is the branch instruction. So now what we are saying is, okay, we have a conditional branch, so we want to jump with a certain offset if A1 is equals to A2. This is what the instruction is saying. So in the beginning, it's the same thing. We do this, we fetch the instruction, then we know, okay, the two operands are A1 and A2, right? So we have to load these two because we want to compare them. And additionally, you have to be careful, this offset actually gets a shift by 1. This is just defined in the RISC-V ASA. So the actual offset is minus 16, so we want to jump basically 4 instructions up again, right? So minus 16. So it could be a loop, right? Where we're jumping 4 instructions up again if it's equal. Okay, now the becomes a little bit complex, the data flow. What we have to do is we have to find out what is the new PC, right? So we have to take the PC minus 16. And for that, we are using the ALU. But at the same time, we also have to find out whether A1 is equals to A2. And what we are doing is we are moving the values all in A1 and A2 up here, and there's another unit which do these comparisons, right? So this is basically a comparator which says is the branch taken or not, right? So now what's happening is, so this one would say it's true, which means the branch is taken, so we should do the jump. So instead of going for PC plus 4, we should now go to PC minus 16, right? The ALU computed, right? It has minus 16 in PC, so it computed what is the next PC, PC minus 16. This one returned to us true, and this means this multiplexer is set to take this input, and then the next thing we are loading is actually from PC minus 16, right? So if this one would be false, so if A1 would be unequal to A2, then basically it would just forward PC plus 4, and that would mean the branch was not taken. We are just executing the next instruction. Okay, so I hope this was clear to you and you got kind of an idea, yeah, how the processor is executing the instructions And therefore, we also looked into all these instructions, which you typically find in instruction set architecture, in order to be able to understand why the processor actually looks the way it looks like. And basically with load, store, arithmetic instruction, and branch, we are basically covering all major classes of instructions you find in a typical RISC machine. Okay, so now let's have a look into pipeline processor architectures. So now let's do a comparison, a step back. So let's first look into the single cycle again. So the idea of the single cycle was we have maybe two instructions, one add, one store word instruction. Then in the first cycle, we would do the add instruction until it's complete. And then in the next cycle, so clock cycle 2, we would do the store word instruction. But the problem is this add instruction can be quite complex, right, in the store word instruction. So the time to execute can be quite long. Therefore, these clock cycles become quite long. And it means the processor runs at a very low frequency. And therefore, usually people now move to this pipeline design, and most processors have this pipeline design. So what you're doing is you're breaking down the instructions into different stages. And if you take an example here, the add has different stages. In the first stage, in clock cycle 1, it would be parts of the add instruction, next clock cycle part, next clock cycle part, and so on, right? But as soon as the first stage of the add instruction has been executed, it would actually move to a next stage in the pipeline. So the store word instruction can already start because whatever the add instruction did in the beginning is now doing something else. So now the store word instruction can do what the add instruction did in the beginning, right? And so first of all, it seems now first longer, right? Because the store add instruction now takes 5 cycles. But if you look into this, every cycle you can put in a new instruction, right? So as soon as the instruction is filled and running, you can basically still do one instruction per cycle, right? They are just kind of here computed in this interleaved fashion. And you can see here, so this example, it would be 5 stages, right? That the instruction is separated in. And this is also kind of a very typical and academic design. So there's a very standard 5-stage pipeline for RISC processors, which is often used in teaching. And we will also use it here in this course. But it's actually also a design which is actually industrial relevant. So there are also real-world industrial processors which basically implement this 5-stage pipeline design. And normally the case is the more high-performant a processor is becoming, the more stages you're putting there, right? So the very, very small, deeply embedded low-power processors might only have, for example, 3 stages. Then these 5 stages are kind of typical embedded processors you might find. And then if you move on to more performant processors, they might have 8 stages, even 12 stages. And then they might also have not only a single pipeline, but they might have several pipelines to do different things. So actually the instructions also start to be executed in parallel. Okay, but we will here look into this very typical academic 5-stage pipeline. And now let's look what are these 5 stages, right? And here, this is now not the full processor design anymore. This is just a depiction which tells you what is the flow of data and what is happening in each stage. But you already know it from the single processor design, or single cycle processor design. So let's just go through it, right? So we have an instruction fetch where you have the instruction memory. So you take the PC as an address, you get the instruction. And now the issue is, since this is a new clock cycle, right? You have to store everything in a register. So there are, between each pipeline stage, you have registers where we're storing the result of a certain stage. So now we're storing the instruction into this register, and it's called the IFID register because it's the register between the instruction fetch and the instruction decode stage. Then you do the decoding of the instruction, and usually in this decoding, you're also reading the operands from the register file, from your registers. These you're storing again in registers. These then will get forwarded to the ALU. This is the execute stage where you're executing the operation, right? Then you're reading this again into registers. Then you could, for example, do a data access to the data memory, either read or write. And finally, you're storing the result and write it back to the register file. So this register file is of course the same as this one, right? So this just represents, here we do the read accesses, and this is the address where we want to do the read accesses to. And this is actually the write access, but into the same register file. So it's depicted here twice, right? Instead of having like here, this one, the error going here and saying here we're feeding the value back into this register file. So we have these stages: instruction fetch, instruction decode, execute, memory, write back. These are these typical 5-stage RISC pipeline. Okay, let's go on and have a little bit of a closer look for different instructions. So let's start with an arithmetic logic instruction, right? Instruction fetch is easy. You have the PC, you're loading the instruction. Then, of course, you do the decoding, you find out, okay, these are my 2 operand registers I have to read, so you're forwarding now these 2 operands, and you're forwarding this to the ALU in the execute stage, and you do the operation like add, sub, or whatever, right? And then, this is also special, right? The arithmetic or logic operations, they do no interaction with memory, right? Only load and store have interaction with memory. Therefore, they just bypass this stage, and then they move into the write back stage here. Right, so there's nothing which is happening here. Right? So sometimes in this pipeline design, some stages are unused by an instruction. So if we have a load instruction, right, the same thing, you know it already. We do the instruction fetch, we get the instruction, we do the decode, we get the register, we get the offset for the address. Then we have to compute the address, which is register plus offset in the ALU. Then we obtain our address, we put this address to the data memory, we get a value back from the data memory, which we are reading, and we put this into the register file. All right, so this load instruction, again, as the arithmetic instruction, can be broken down very nicely into the different parts it does in the pipeline stages, and this one actually requires all stages of the pipeline. Store, similar, right? We do the instruction fetch. Now we again have the offset, the base address, but we also have the value we want to store. So we're computing the address we want to store to, and then we give the address plus the value we want to store to the data memory. And now, if we look into it, right, this one does not use the write back stage, right? So the store does not write everything to the register file, so basically this one is kept empty. Nothing is happening there. Right, and this, the final one is in the branch instruction, right? So in the branch instruction, as we know, we are doing the instruction fetch, then we basically take the PC and the offset. There might be some comparison happening, so it's also omitted here, right? You compute PC plus offset, and this gives you the new PC, right? And there you see, actually, you don't need memory nor write back, right? Nothing is happening there. Okay, good. So basically, this hopefully showed you how these instructions can be broken down into the different operations they are doing in each stage of this pipeline. If we go back and look into how the design would look like, right, we would come up with something like this, right? So now the PC would be given an instruction memory, the result would be given into these registers, then you would do this decoding, you have the sign extension here, right? And you give it again to register, and that is the ALU with the multiplexing, and later on you have the registers, data memory registers, and then the write back. So this is more of a structural view, which basically would allow you to run the standard RISC-V instruction set, all the integer operations, now in a pipeline fashion, right? So what's happening is it really ticks, right? So the first instruction is here, then it moves here, and then the next instruction comes here, right? So as it ticks, the instruction gets executed, right? Per cycle. Okay, the issue is, right, as I said, is when the pipeline is filled, we can run one instruction per cycle, right? We can always put a new instruction into the instruction fetch stage because the previous one went into the instruction decode, and then it goes on and on. But actually what's happening is this is not always possible. So the issue is in this pipeline there can so-called hazards, and these hazards prevent us from reaching 1 cycle per instruction. All right? And there are 3 types of hazards. One is the structural hazard. That means in 2 stages you're actually using the same resources, and therefore you have a conflict with this resource and only one of the stages can use it and the other one has to wait. Then we have so-called data hazards. So the problem is there is some data you want for the computation, but it's not yet ready. So you don't find it in the register file. So at the moment you can't use it. You have to wait until it becomes available. And the third one is the control hazard. That means you want to fetch a new instruction from a PC, but you don't know which program counter you should fetch the instruction from. So you have to wait until you know what is actually the new program counter, and only then can you go and fetch the instruction. And now let's have a more detailed look into these 3 types of hazards we find in the pipeline. The data hazard is the first one we can look into, right? So it's very clear. So we have there are 2 different situations. One is we have an ALU operation, or so an arithmetic operation after a load. So let's have a look, right? So we do a load, and we want to get the value from the address A4, and we want to store it into A1. Right? Then in this stage, here in clock cycle 4, we would load from the data memory, and in clock cycle 5, we would write it to the register file. But if you look into this add instruction, that would enter right here already in cycle 2. It would start with an instruction fetch, right? So because the instruction fetch here is used in cycle 1, and instruction fetch becomes available, then in cycle 2 it's used by the add instruction. And in cycle 3, the add instruction wants actually to read its operands. But the operand you're having here, A1, that is still under load. You don't know the value yet, right? Because it gets written here, you get the loaded value. So now you have 2 cycles, right? 2 cycles earlier you want to have this A1 before it gets written to the register file. And therefore this is the data hazard, right? So if you would read A1 here, it would not be the up-to-date value. Then you would not execute this program, because if you execute this program, the way it's written here, it means this A1 you're adding here is the one you loaded from here, because this instruction was defined to run before this instruction. And this is the issue due to this interleaving of instruction, that you run into this problem that you have this data hazard. Okay, so now what can we do? So the easiest way you can do is deal with this is you don't know it, right? But you can detect that this is not up to date, and now you just have to wait. You will take the add instruction, you say, okay, this is called stalling the pipeline. So you're stalling the pipeline for 2 cycles where nothing is happening. So all other instructions also have to stall, and then you do the instruction decode stage only when you know the A1 is up to date, and then you can run the add instruction. But this now means the add instruction from the outside, it looks like this add instruction now takes 3 cycles, right? Because it finishes 3 cycles after the previous instruction, not 1 cycle anymore, which we wanted to have. And this basically means our cycles per instruction is now a little bit lower. It's not a 1, so it might be some other value. There's a second way to deal with this, and this is to improve the processor. So one thing you can do is you can say, actually, when you look into it, this value A4, you don't have to wait until you write it to the register file and then read it back from the register file. So this is what we did here, right? So we write the value to the register file, and then we read it back into the register in the pipeline register. But A1 is already known here, right? You have a copy of A1 in this register, so 1 cycle already earlier. So what we can do is, and this is called a forwarding path in the microarchitecture, we take the value from A1 we have already here, and we forward it right to the ALU. So because you already have it, you don't have to. We don't write it to the register file and then read it from the register file. We basically make a forwarding path where from this memory write-back register, we bring it to the ALU. And that saves you 1 cycle. You still need 1 stall cycle, right, to do it. But instead of having 2 stall cycles, wait cycles in this add instruction, now you only have 1 cycle. Therefore, most processors, most industrial processors have this forwarding path built in. in order to run the programs faster. Because this is often an issue that you load something and then you want to right away do an operation on it. Okay, the same thing actually happens when you do two ALU operations after each other, two arithmetic operations. So if you do the sub, and the sub computes a new value for A1, so A1 is A1 minus A2, and then you want to do an add operation, and of course this A1 here, this value is the same as the one you have written here. And the same thing happens, right? A1 you only know in cycle 5, but the add instruction already wants to read it in cycle 3. So again, we have a data hazard, and we have an issue. So now what you can do is, again, you can stall a pipeline for 2 cycles, and then you would write the value to the register file, and then read it from the register file. And this gives you, again, 2 cycles, so it looks like the add instruction takes 3 cycles instead of 1 cycle. But here the situation is even better. So if you look into it, we see this result we actually already have here, right? So we just copy it into this register in the register file. But we know it already after the ALU operations. Already in this stage we know, okay, there is what is the value of this subtraction. So we should actually also put in a forwarding path. And here you can put in a forwarding path that from the XMEM register you're going right into the ALU. And the nice thing about this thing now is we don't have any stall cycle anymore. So we can take a value as an operand right after it was computed from other ALU operations, and we don't see any additional delay. So again, what's happening is most or almost all embedded processors have this forwarding path. Now, even if they have a 5-stage pipeline, they have this forwarding path, so you don't see any additional delays when you're doing this operation. Another way of dealing with this is if you don't have these forwarding paths, then the compiler has to make sure that it kind of looks for instructions it can put in between which don't have these dependencies, right? So the problem is there's a dependency that whatever you want to use here is computed here. But if you would put some instructions in between, you could break these dependencies, but it's not always possible because usually, as I have said, when you do some computation, you want to take the result and do right away some other computation with it. So these dependencies are actually happening very, very often in the programs. Okay, but this gives an idea about the data hazards and how to deal with the data hazards, right? So what we see is in modern processors, between ALU and ALU operations, usually a forwarding path to make sure you have no additional delay. But if you do a load, then usually you have some additional cycle you have to wait for until the result becomes available, right? And then you possibly have to stall a pipeline if you want to use it right away. Okay, the next thing is the control hazard. So the same situation actually applies. So we want to do a branch instruction, and the issue is, right, the branch target we are computing in the ALU, right? We're taking the PC plus the offset. That's where we want to jump to. But so if you take this branch, where to jump to, you only know in cycle 3. But the issue, of course, is in cycle 1, you already, or in cycle 2, the next instruction already, you want to fetch the next instruction, but it's not possible because you don't know whether you're jumping, and if you're jumping, where you should be jumping to. So now you have an issue that you cannot do the fetch because you don't know what to fetch, right? And therefore, basically, after a branch, right, you usually have to do at least 2 additional cycles in order to know what is the branch target, and then you can continue execution. So actually, very often in embedded processors, this is how it's designed, that if you make a branch or a jump, actually this costs you virtually 3 clock cycles because the next instruction has to wait 2 more cycles before it can get started, because then you know the PC. We will also see there are some ways to kind of also get across these control hazards we will later discuss. Okay, the last type of hazard we want to talk about are the structural hazards. This has to do a lot with the pipeline design. So in the usual RISC-V pipeline with Harvard architecture, this doesn't happen. It can happen when you have a von Neumann architecture. So what's happening is, if you want to read, if you have a von Neumann architecture, the data memory and the instruction memory use the same read interface, right? So you cannot read from a load some data value and at the same time fetch the next instruction. So there would be some instruction, of course, coming here would be an instruction fetch here, an instruction fetch here, which I haven't shown. But then you also want to do an instruction fetch here when the load instruction is in the memory phase. And this instruction fetch, then you have to delay because you first have to load this data memory before you can use the next instruction fetch. So these structural hazards then cause you to wait. But this is something which depends how you really do the architecture of your process, and only if you really have a shared resource which is used in several stages. So here it would be the memory interface. So reading is used in the mem phase and in the instruction fetch phase. Then you have to do some arbitration and say we first run this one and the other one has to wait, and then we run the other one. Now, but of course, for more complex processors, you find this in different positions where you have shared resources. Okay, now how can we go on and improve the performance? All right, so what we already have seen against data hazards, we can use this data forwarding and the forwarding paths, right? And this just removes these stall cycles, and this gives you a higher performance because you have less waiting cycles in your execution, right? And the next thing you can do is a so-called speculative execution. That means if you have these control hazards and you don't know where to jump to, you can do, for example, some branch prediction and say, okay, I'm trying to predict where I have to jump to, and then start executing this branch. If the prediction was right, you can just continue the execution. If the prediction was wrong, then you, of course, you have to remove the instruction you have already loaded, and you have to fetch the new instructions, and this is called a pipeline flush. So you're flushing the pipeline for the instructions actually you erroneously started to execute, and then you're just starting to do the other branch. So for example, one idea would be you're always saying, as a branch prediction, you could always predict I'm not taking the branch. So if you're not taking the branch, you already know what is the next PC, because it's just PC plus 4. So you could just continue the execution, and you'll find out, oh, I'm really taking the branch. Then you're flushing out these instructions you already have loaded, and you're making the branch jump and start with the new instructions. And this just saves you. So if you take the branch, it would be just like the branch takes 1 cycle. If you don't take the branch, then it would be the 3 cycles, right? Because you are basically removing the 2 instructions you already have loaded erroneously. Okay, good. So this was to improve the performance, right? And with that, this gives you kind of an idea how a pipeline processor works and what kind of hazards you have there. So, okay, so now if you have a program, of course, you're interested in how long does it take to run this application, this algorithm, this task on your processor. And of course, what you can do is you can use different tools. You can use simulation to find this out. Or another option is that you do kind of a quick estimation. For example, if you just want to find out, should I be using this microcontroller, or should I buy a microcontroller with a bigger core, which has more performance? You can do some quick estimation based on what you know from your application. These quick estimations, of course, are not too accurate, but they indicate you whether you're kind of in the right order of magnitude in saying, you know, this, I want to execute this in 2 milliseconds. Do I reach these 2 milliseconds or not? The other thing is, of course, if you're designing a real-time system where you have very strict deadlines, then, of course, and these deadlines you have to keep for any execution of a certain task. Then, of course, you have to go and take a dedicated worst-case execution time tool, find out what is the worst-case execution time for this program, and make sure that with this worst-case execution time, you can always meet your deadline. So this is more now something where a kind of quality of service, where you're saying, okay, I actually want to do some task. It's not like super critical that it's in a deadline, but I want to know am I more or less in the range where I think this system would work well. So and now what I want to show you is how to quickly do these estimations based off what you know from your processor at a very high level. So the first thing is, or the first formula which is important, is if you want to get the execution time, it's actually very easy, right? If you're saying there's one cycle per instruction, you just take the cycle time, right? For example, 10 nanoseconds, whatever you have them, and you're multiplying this with the number of instructions. Now what's usually happening is your processor will not do one instruction per cycle, especially if it's a pipeline processor. We know there could be data hazards, there can be control hazards, and so on. And therefore, it will actually be a little bit lower. And then usually what you can do is, for certain processors, you basically know more or less what the CPI could be you expect. So it could be like you're taking 1.3 cycles per instruction. So what you're doing is you're taking this value and you're scaling it with this estimated CPI you're expecting to get. And this gives you a rough estimate. That's my execution time. Now let's have a closer look into these three factors. So what is influencing these three factors? So first of all, of course, your algorithm, right? There are certain tasks you can do. You can use different algorithms. For example, Fourier transformation. There's a whole range of algorithms to do Fourier transformation. So which one you choose depends then how many instructions you actually have to execute. And it has also some little influence on the CPI. Just with the mix of instructions you're getting. Do you get more loads and stores? Then the CPI might go up and so on, right? The next, of course, important thing is what programming language do you choose. So the embedded domain, it might be, do you do the programming on assembly level, or do you do it on C, or do you do it on C++, or if you have a bigger system, you might actually also do something like Java. And this programming language, of course, due to the compilation process, will have some big effect on the number of instructions you have to execute, and also on the instruction mix. So again, it's CPI a little bit. Then you have your compiler, right? And the quality of the compiler actually also influences these two factors. And not only the compiler, but also what settings you're doing, right? So if you take the compiler and you run, for example, GCC without setting the optimization level to a high level, so say it's called an O0 for GCC, then you will actually execute a lot of instructions because the binary is not very much optimized. While if you go to O3, which is the highest level of optimization for your compiler, then you might actually see a very low number of instructions. And the same is again for CPI, right? But these are always not that big influences of CPI. Then, of course, you have to say what kind of ISA I'm taking. So do I have an ARM core, or do I have a PowerPC core, or do I have an ARX core, or do I have a RISC-V core? And this also kind of has influence on the number of instructions, on your CPI, because the pipeline has to support this ISA, and of course, also on the clock frequency. How complex is the instruction set, so what frequency will the processors run in? Then you have your microarchitecture, so do you have 5 stages of pipeline, do you only have 3 stages of pipeline, and so on. And as we've seen, of course, this has influence on the CPI very heavily because the hazards depend on your pipeline structure. And of course, the more stages you're having, the smaller these stages are becoming, the higher you can do the frequency, the faster is your processor. Finally, the implementation. So do you go and do this in a 32 nanometer process, or do you do this in a 16 nanometer process, right? FDSOI or FinFET or whatever you're choosing. This, of course, has big influence on your clock frequency. And then there's one other factor which you should not underestimate, which actually is becoming now also a very, very dominant factor. And this is your memory system. And we have not looked into the memory system at all, and we have to do that. So the issue is, we always said load and stores take us 1 clock cycle, but that is actually not true. It depends where your data is. And this depends whether your data is in cache or your data is into the main memory and so on. So, and this has very, very big influence because sometimes you have to wait very long for the data, and this actually gives you then a very, very heavy hit on your CPI. Okay, now before we go into the memory system, so the next thing you can do is you can say if you know a little bit more about your instruction, you did a little bit about your program, a little bit of instruction profiling, you can also take this CPI and you can say, for different instructions, they have different CPI, right? So load or store instruction might have a higher CPI because of the memory system and so on, but we will later see we can also estimate this differently. And other instructions like ALU instruction always take 1 clock cycle. And with that, you can then do your estimation. Okay, I jumped over one slide. Okay, this is. So let's first do a little bit of estimation. So let's say we have a processor that's running at 50 megahertz. And it has, we do 10,000 instructions which take 1 clock cycle. We have 20,000 instructions which take around 1.7 clock cycles. And we have 10,000 instructions which will take 1.7 clock cycles. Then we just take the cycles are 10,000 times CPI 1, 20,000 times 1.5, right? 10,000 times 1.7. These are, so we will execute 57,000 cycles. And we divide these 57,000 cycles by the frequency, and this means this program will run in 1.14 milliseconds. Okay, and now, as I've said, that's already nice, but the memory system is an important factor. So now, why do we have at all a memory system? So the issue is, we have our processor, then we have, in the processor we already have memory, which are registers, but these are the most expensive, so it's very easy and fast to access them, but they are very expensive. Then on the next level, usually we have some caches. The caches are usually on-chip SRAM, embedded SRAM, so they can be accessed very fast, and you can see these are already kind of very old numbers, but they show you relatively what's happening is you can access them very fast, right? But they're also very expensive, right? So you can't put a gigabyte SRAM on your chip. Much too expensive. So these SRAM caches must be very small. And therefore, what you're doing is you have some main memory, which is DRAM, which is off-chip. It's an extra chip, which is a DRAM chip, right? Then you have more access time to get to this chip, but it's very cheap to put a lot of memory. And therefore, we build up this memory where we have caches, and we have some main memory somewhere. And of course, there are now a lot of ways how to integrate this. So for example, there are 3D chips where you put the memory. You have a chip with the processor, you put another chip on top which has the memory, and then you have very good bandwidth to this memory chip, and then you can get a lot of data to your chip very fast. And that's actually this kind of memory computation integration. This is now where people think, and there's a lot of research at the moment happening where people think we can get a lot of performance out. So we're now losing a lot of performance just for moving the data, not for doing the computations. So now there's a lot of effort in getting the data more efficiently to your computational units to do it faster. Now we will only look into more traditional designs, right? So the traditional design could be something like this. You have your RISC processor. The RISC processor is connected to 2 caches, one for instructions and one for data. They are very fast. Then you might have a second level cache where you have data and instructions stored on chip. So this is your microcontroller, for example. And then there is an interface, which is also called memory controller, where you go to some big off-chip memory. And that would be, for example, a typical design of a memory hierarchy for a simple controller. Now, if we look into these memory systems, now we have to look and analyze what is the data movement we are having. So usually what's happening is you're not moving single data words, so one variable from main memory to your cache. Rather, you're moving a complete block of data, several instructions to your caches. And this is called kind of the block, right? This is the minimum line you're actually transferring. And then we have to think of, what are the hit and miss rates, right? So we have to say, okay, how long does it take us when we find, this is a hit, when we find, for example, the data in the cache, how long does it take us to get this data back when it's cached? And the miss rate then tells us, okay, the T-miss, actually the miss penalty tells us what is the additional time it takes us when we want to access the next level, so the L2 cache or the main memory, right? How much time does this cost us? And then, of course, which is very important, is how often do we find the data cached? And this depends on how you organize the caches and how big they are. So in 80% of my memory loads, I actually find the data in the cache. and 20% they have to go to main memory. And you will have a lot of different timing if you actually can achieve that 90% of your accesses actually are cached, or you find the value in cache, and only 10% go to main memory. So as I said, there's a lot of performance can be gained when you are able to make sure that the data the processor needs is already very near to the processor in one of the caches. So let's look a little bit, we don't go in so much into details how caches are organized. There are kind of three classes of caches. Usually they are called so-called directly mapped caches. That means if you have a certain address, there's only one location in the cache where you can find this data. So you only have to look up one location. But of course, it's not very flexible, right? So if you want to keep some data into the cache, you always have to make sure if it's from this memory address, you can only keep it at this location. If you just don't need anything which is mapped, all the addresses which are mapped to this location are not required. You cannot use it or not cache it there, right? Therefore, you can go and say, I want to have more flexibility. So more flexibility would then be a so-called set associative cache, which means there's more than one location where you have to look, is the data there? You can store it in different locations in the cache. And then there's the so-called fully associative caches where you say you can store a certain address in any location in the cache, which is of course the most flexible way. That means you get the most hit rates, but the lookup is more important. So now you have to look up at every location in the cache, is my data there? All right, so it's an issue between being flexible to store the data and cache it, and how complex, of course, the lookup becomes to find the data in the cache. Then we have a problem which we have to deal with, which is cache consistency. For a single processor system, this is quite easy. If you go to a multi-processor or multi-core system, this becomes more complex, because then you have to say maybe some data is only at one core cached. What happens if another one wants to use it, right? Then you have to look up whether it's cached somewhere else. So cache consistency for multi-core systems is quite complex. For single-core systems, there are basically two main ways to make sure that cache consistency is preserved. One is so-called write-through, so that the problem is always if you're changing a line. So let's say you're having a certain piece of data, you have it in the cache, you're changing it, then you have a changed value in the cache. If you now want to load a new value into this cache line, you cannot just overwrite the changed value, because then you would lose it, right? So this means the cache line is dirty. So you have modified this cache line, and it's different from what you find in main memory, because you have worked on this data. So the one thing we can do is write through. That means if you're writing, you're always writing to the cache and you're writing to the main memory, such that the main memory also has always the up-to-date value for each cached block. And the other thing we can do is called write back. So if you find out that you want to evict, also remove a dirty cache line from your cache, then you can say, okay, this line is now dirty, so I have to first save it to the memory before I can bring a new block of data into the cache, which overwrites this data. All right, and with one of these two policies, you can always make sure you're keeping your cache consistent. There are two other terms which are called split cache or split memory. This just means, if you go back to the original picture, we had there one instruction cache L1, one data cache L1. So this is a typically split cache, the instruction and data kept separately. While, for example, the L2 cache was shared, and then it's not a split cache, right? And you can even have split memories where you have different memories for instructions and for data. Okay, and now let's say you have a certain microcontroller, you know the CPI, you know the memory hierarchy of this microcontroller. Then again, you can make kind of a quick estimation. How long does it take your program to run? And what you have to do is, you first have to find out how many cycles do I have to wait when I'm accessing the memory, right? So for example, you have let's say I take an example, we have one cache and one memory. So in the beginning, right, what I said is, we always assumed load and stores take one clock cycle. Yeah, but especially if you have a load, you have to basically wait until you get the data back, right, before you can use it. Therefore, then you have to say how many cycles do I have to wait until the data comes back. And for that, you can just use the hit time, which is the time until you get the data. Or if you are missing the cache, you take the hit time plus the additional miss penalty. This is just a definition, as I said. The miss penalty, this extra time you have to wait to access the memory, this gets added to the hit time. And this is your access time, and then you divide the one clock cycle you're already having. So you take the access time minus one clock cycle. This is the clock cycle you always have to access the memory. You divide it by the clock cycle, and these are your additional wait cycles. So, and then you just have to find out how many accesses do I have. Then you take these accesses times the wait cycles, and this gives you the number of stall cycles you're actually waiting to get your data. Right? So for example, you can say the number of accesses are all my load and store instructions, and then you say, okay, how many of those are at the cache? So for finding out how many cache, you take the hit rate in the cache. You say you have, let's say, 100 load and stores, and you have a hit rate of 80%. Then 80 of these load and stores will be in the cache, while the other 21 will be in the memory. So you have to take the memory, these are then the memory instructions. And then finally what you're doing is we're taking our original formula, instructions times CPI, maybe for different types of instructions, and we're adding all the cycles to it, which are the cycles for waiting until the data comes back from the memory. And this gives us the number of cycles to execute the program. We multiply this with the clock time, and this gives us then the execution time on this system. Okay, let's take an example and go through it. All right? So we have a clock frequency of a 50 megahertz processor. That means we have a clock time of 20 nanoseconds. Again, we have the same thing, right? We had 10,000 instructions, which are of the class with a CPI of 1. We have 20,000, which has on average 1.5. And we have 10,000 with 1.7. So normally, if we don't ignore the memory system, then we will have 57,000 cycles for execution. Now what we are saying is, okay, let's look in the instruction fetch, load, and store. Say how many, so all of them, right? All 40,000 have to do an instruction fetch. We have 8,000 load instructions, we have 5,000 store instructions. These are our miss, right? So only 2% of the instructions we don't find in cache, we have to go to main memory. 4% of the loads, 4% of the stores. If we are missing, we have additional miss time of 520 nanoseconds, right? Which basically, if you say 20 nanoseconds our clock time, relates to about 25 additional cycles to get the data, right? So if we have 40,000 from those 2%, then 25 cycles each, actually we get another 20,000 cycles where we're waiting for data, 8,000 cycles where we're waiting for load instruction, 5,000 cycles for the stores. So we're taking the original cycle count, 57,000, plus 20,000, plus 8,000, plus 5,000, and then we divide by the clock frequency, and this tells us now we have 1.8 milliseconds, right? And if we did not have the memory system, if we assume all the data just gets to the processor in time with one clock cycle, we were at 1.14 milliseconds. So in this case, but it's maybe also very, very worst case scenario, actually you get a 60% execution overhead, right? So you would be very, very optimistic if you would estimate your execution time without memory system, because actually 60% of the execution time you're just waiting for data. So you have to have some estimation on what you think would be the memory system influence be, right? So it's quite important to consider it. Okay, now we do the same thing, right? But the only thing we are doing is now we are doubling the clock frequency. All right, so now we are doubling the clock frequency. And what we would expect is now we should be 50%, we should actually factor 2, right? We should be 2 faster, right? But the decrease is only 31%. So why is that the case? So the case is we only increase the clock frequency of the core, but the access times to the memory is still the same, right? Therefore, if you scale up the frequency, those access time to the memories will not go up, right? So the cycles will be shorter, right? So what actually is happening is suddenly now we are having more wait cycles because now we're still waiting the same time, just the clock frequency is higher. Therefore, kind of the clock is ticking faster while you're waiting for your memory data to come back, but it's still the same waiting time, right? Because that is basically limited by whatever memory technology you're using. Right, so and therefore just scaling up frequency of the core, but this is also limited again by the memory system. So at some point, just trying to get the core to run faster will not help you. Then you have to go back and say either I have to improve my memory system in terms of structure, so I'm getting more data cached and I have less cache misses, or I have to go and move and say I need faster memory in order to be able to actually increase the performance of my system. Okay, so this was it on the memory side. Still, of course, if you go now to more high-performance computers, you would go and work on the memory side, but you also work on the processor. And what's happening is if you're now moving to, let's say, processors where you want to be very, very fast, you actually take the CPI and you want to get the CPI below 1. Right? So you want to take maybe 0.6 cycles per instruction. And how can you do that? You can do that by executing instructions in parallel. And there are 2 ways to do this, right? This is called a multi-issue processor. And this multi-issue processor just issues more than 1 instruction per cycle. And there are 2 ways of doing this. One statically. And if you have a static multi-issue processor, this is what is known as a very large instruction word processor. So basically what you do is you put 2 instructions next to each other and both of them are executed, right? You're fetching 2 instructions at the same time that the compiler put next to each other and both of them are executed. And right, and this is of course only possible if they don't have any dependencies. If they can be executed in parallel, independently of each other, and you get the results of both of them back. So the compiler decides which instruction it puts in parallel, right? So this is static. And the other thing is, of course, you can have a dynamic multi-issue processor, and this is what is called a superscalar processor. And this processor just fetches more than 1 instruction, so it fetches a complete block of instructions, and then it finds out what the dependencies are, and then it's feeding the instructions into more than 1 pipeline, so more than 1 parallel pipeline, and so tries to get the CPI below 1. And this, of course, then gives you a very high-performant processor. But then again, the same issue, of course, the processor can execute the instructions very fast, but still you need a memory system which is able to bring the data to this processor in order to process it also very fast. So then caching becomes even more important. And what are these processors basically exploiting? They are exploiting parallelism in your application. And there are kind of 3 levels of parallelism. One is instruction level parallelism, which I tried to already say. It's you have 2 instructions and they don't have any data dependencies. They're working on different sets of data, so you can just put them in parallel. And then there's something which these processors are doing, which is called loop pipelining. So what they're doing is, if you execute 1 iteration of the loop before it has finished, in parallel, they also work on the next iteration of the loop. And this, of course, also only works if there's no data dependencies between your loop iterations. And the final thing is, of course, what you're having now, of course, in multi-threaded processors, that you actually have different threads running, and then you can take some instruction from one thread, some instruction from the other thread, and execute them in parallel because these are independent threads from each other. Okay, great. So I hope this gave you a little bit of an idea how you can get to a quick estimation of execution times if you have some basic idea how your processor and memory system is built up. And as I said, this kind of tells you when you have to select a certain processor, is that fitting for my application and my use case, or do I have to maybe go for a more powerful processor in a very early concept phase. Okay, so next to processors and memories, what's also very important if you're designing a system on chip is that you look into your on-chip interconnect, because also the on-chip interconnect decides how much performance your chip will be having. So you need the bandwidth on your interconnect to be actually able to transmit all the data you want to transmit between different modules. And this, traditionally you use so-called buses for this, on-chip buses they're called, which are wire-switched interconnects, and we will have a close look here in this session how they are working and how they are internally built up. And you still find them in a lot of different applications, especially if you go to microcontrollers, embedded applications, low power applications, you find these on-chip buses. There is now a second type of interconnect, which of course in the last years became a very hot topic, or actually already a decade ago became a very hot topic. This is networks on chip. So the problem was for very complex chips, for example, if you think about a 5G modem chip where you have all these different modems for 5G, 4G, 3G, plus maybe some audio processors, plus some video encoders, video decoders to be able to watch videos on your mobile device, or take videos from the camera with your mobile device. That becomes, you have to connect all these things together, and then actually it turned out that these buses are not the best way of doing it anymore, and therefore they moved to this network on chip principle, where they're actually kind of mimicking what you have on the internet with different routers on a single chip which you're building. Right, but before we go to these complex interconnects, right, first you have to understand, how does a simple on-chip bus work, and what do you find internally in there, and this is what we are addressing here in this session. So let's have a look. Usually what we are now looking into are so-called memory map buses, which mean the purpose is you're reading and writing to a certain address, and this value could be in this address. You could either find memory, but you could also find some other device. So it could be an I/O device, or it could be a hardware accelerator or anything, right? And you have to be careful. So the complete interconnect is called a bus, but actually it consists of different groups of signals, and these group of signals or sub-buses are also called bus, right? So there is, for example, an address bus, right, which is a group of signals which are carrying the address. There is a data bus for reading data from a memory or device. There's a bus to write data to a device, a group of signals. So if you have, for example, a processor which is reading and writing words of 32-bit, these data buses will have 32-bit width, right? 32 wires to transmit this value. And then additionally, there are additional control signals you need to implement some bus protocol, so the device knows now I actually have to transmit data. Now there's a request to read data, now there's a request to write data, and so on, right? And the modules on a bus you can separate into initiators and targets. And the initiators are the ones who usually request a certain communication to happen. Previously, this was called master and slave. But the new terminology, which is now basically taking over this a little bit, to be politically maybe more correct, is that we're now calling them initiator and target. But if you talk with other engineers, you will also often hear these master-slave terms. Okay, and what are typical initiators? Typical initiators are processors like CPUs, general purpose processors, digital signal processors, DSPs, then often DMA. So DMAs just transfer data, so they just request to read data from somewhere and write it somewhere else, so they are initiator when they're doing that. And then other initiator might be, for example, also bus bridges, that there is some other bus system which bridges to your bus system, and from this other bus system comes a request and gets forwarded to your bus. And typically targets, very classic, of course, memories, which are just storing data, but then, for example, also accelerators, which can do some computation for you, interface peripherals, I/O peripherals, and so on. Or again, of course, if you want to request from another segment, also a bus bridge can, of course, be also on the other side, be on target. Now, what classes of buses you're having? This depends on how many initiators and how many targets you're having. So if you only have a single initiator, so just a processor, and that processor is the only one who's making requests, then you're building a single initiator bus, right? There's only one initiator on this bus. If you have several initiators, then there are actually three architectures. So one is a shared bus, which means the bus is shared between all initiators. And only one of the initiators gets the bus and can do a request. If you have a layered bus, then what you're doing is you're putting the targets on different layers, and then as long as initiators are requesting a target which is on a different layer to communicate with it, there are no conflicts, and the two initiators can do their requests or their accesses in parallel. But if you want to request, if both of them are requesting a target which is on the same layer, then actually these accesses have to be arbitrated and will be one after the other, so they are blocking each other. And then there is a so-called crossbar, which basically means that every target can be accessed independently. So each initiator can just access any target. Only if they want to access the same target, then of course one of them has to wait until the other one has finished. Okay, now let's start with the most simple bus, which is the single initiator bus, right? And now if you look into, for example, some SOC data sheets, you often find something like this, right? So there is some structural block diagram which saying, for example, this would be a processor. It says, okay, there's an M3 processor, there's some interconnect in between, and then you have some memories and accelerators and everything here, right? And then you have kind of this arrow here, and this depicts there is an interconnect. But actually it doesn't tell you what kind of interconnect this is and what kind of circuit this is, right? So a processor is a digital circuit. A hardware accelerator is a digital circuit. A memory is also kind of a digital circuit with, of course, their special memory cells, right? But what is a bus, right? And it's basically, it's wires mainly, right? Because you're transmitting data over the wires, but you also have to do some operation on these wires and say what to connect. And this is also done by a digital circuit. So basically this bus, you could also just express it. It's the same kind of circuit and technology you're also using for your other devices like your processor. So now, usually what you're saying is you put all the signals for the bus together in one protocol, which basically means there is an interface for initiators, and on the other side there's something which is called the mirrored interface, right? So every signal which goes out of the initiator has to go into the bus, right? So here it's mirrored. And then we have the same group of signals which is the target interface, and there is a mirrored target at the bus side, right? So everything that goes into the target has to come from the bus. Right, so this is a mirrored interface. And what do you find in these interfaces? You find buses for transmitting the address, transmitting data, and transmitting control signals. Okay, and now let's look how these are arranged. So basically what you can do is, this would be a very, very simple architecture. So the initiator gives an address, and for example, it can also give data it wants to write. And then there are some control signals like select and write read. And with this, it indicates now I want to do an access. It's a write or it's a read. Then the target, if it's a write, the target can just say, okay, this is my address. So it compares, is this my address? Each target has a different address, or actually range of addresses. If it's my address, then I have to service this write request. So for example, I have to save it in this address if it's a memory. Now, this is easy, right? What's happening if there's a read? So if there's a read, basically target 1 knows, okay, I'm now reading, the initiator wants to read a value from me. So I take this read value and I put it on the read bus. Now, of course, the initiator has to know, or has to read this value, right? But then these are all digital wires, and basically only one of these wires can drive the input of the initiator, right? So it's a standard digital circuit. Yeah, this is a standard digital signal. So what you're doing is you're putting in one multiplexer. This multiplexer also knows which target was addressed, so it also needs the address to find this out. And then, for example, if it finds out, okay, target 1 was addressed, it will just forward the answer from target 1 to the initiator, and target 2 and 3 values are basically stopped here, right? Because we're not interested in them. And this simple digital circuit will already tell you how this interconnect here is structured, what to find there. Now the idea is, of course, you need to define a protocol between the target and the initiator to say how does these transfers happening. And therefore you're having all these signals, and you have the additional control signals to say what the protocol is. So for example, let's say we want to write, right? So if you want to write, then you have to set the address, and you have to be careful. So the address is coming from the initiator to the target. So the initiator is setting the address. The initiator is putting write read to 1, which means this is a write access. Then it's putting select high, which means now I want to access the bus. And then it puts the write data onto the bus, right? This is what's happening, for example, in cycle 2. So in cycle 2, the access is starting. And now the target has to tell him, now I know you addressed me. I know you want to make a write request on me. And in this next cycle, it says, okay, it is ready. So it means the write access was successful. So it's kind of an acknowledge here, right? And then the initiator can do the next request. Now what can happen is sometimes your targets are very slow. So your target will not be able to service this write request right in the next cycle. But this is not a problem, right? So you're just, it takes actually 3 cycles to service it, so it will just put the ready high after 3 cycles. This means that due to this acknowledge already not coming, right, that the initiator knows, okay, the target has not yet responded, therefore I just keep everything the way it is. I keep the address, I keep the data, and I wait for my target to acknowledge me that it was able to do this write request. So that this one is coming from the target to the initiator. Everything else, all other signals are driven by the initiator side. Now if you make a read access, right, it's very similar. You put the address. Now you put write read to low, which indicates it's a read access. Then you put the select signal high, which says the access should start. And then in the next clock cycle, the target acknowledges by setting ready to high. And then the target also, of course, has to drive the read data bus in order so that the initiator can read the data, right? So you can see the read data bus is also driven by the target to the initiator, and the initiator can just take over this value. Again, what can happen is that the target needs some time to get this value, right? So it will not respond in 1 clock cycle. So again, we have here 2 wait cycles where nothing is happening. And then also, again, the initiator just has to keep the address up, keeping the access high, saying, okay, I still want to do this access. It's a read access, I have the selection high. And then it just waits until the acknowledge is coming, and then it knows, okay, now the data on the read data bus is valid, and I can read it, and this is the response to my access request for reading. And these kinds of protocols are actually, now it's very easy, it's a single master bus, and only reading and writing. But if you go to very complex buses, which have a lot of features we will also look into, these actually protocols become very, very complex. And the issue is the state machines which are understanding these protocols. So the state machines you have here in the bus interface of the initiator and the bus interface of the target, these state machines actually can have a lot of states, and if you are a digital designer, implementing these state machines which understand these bus protocols can actually be some of the most advanced state machines with the most states to deal with than you can design. So it's actually not that easy to design them for very complex bus protocols. Okay, so what is the performance of this simple bus, right? So what is the bandwidth we can transmit? Right, if you look into it, right, we have always one cycle to request a read, and the next cycle the data comes back. One cycle makes the next request, data comes back. Right, so we get one data word back every 2 cycles. Therefore, our bandwidth is the bus width. So for example, if we have 32 bits, then it's 32-bit, right? Times the frequency we're running the bus in, and then divided by 2 because we can make 1 access per cycle. In the following, we will not go into detail and look into the signal ones. We are now doing a little bit of an abstraction, and we are just saying, here we make 1 access to a certain address, and this is the data here indicated by this number and also by the color, which is servicing this address, right? And in each clock cycle. So this kind of saves us a little bit the complexity to really run the bus protocol, but just to say what accesses are happening in which clock cycle, right? And then you can see you always give me the address for 2 clock cycles, and the data comes back in the next one. So every 2 clock cycles you can do an access. Now, the first thing you can do to improve this bus is you can say this bus now should support pipelined accesses. And this means, similar to the pipeline in a processor, you put the address, and in the next cycle you get back the data, but you don't have to wait then, you can already in this cycle put the next address, right? And so you can put address, 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 and then always the next cycle you get back the data. And the nice thing is, now basically what we did is, if you look into it, every clock cycle we can transmit some data, therefore we basically already doubled our bandwidth, right? So this factor 1.5 is now removed. Now with having pipelining in our bus, we can actually double the bandwidth of this bus. But of course, there are some additional control signals required to support this pipeline accesses, which then also means your bus state machines become more complex and your bus becomes a more complex digital circuit. The next thing you can do is, which is also often supported in buses, is instead of doing this pipeline accesses, you are basically saying you have a certain control signal, you say you want to have a burst, right? So what you're saying is you're putting certain addresses, and you're saying you want to have a burst, and then you get the data back for these accesses. And then you optimize it and say, I just take 1 address, and I say it's a burst, and then I get back I get the data at this address, but I also get the data for the next address, next address, next address. So I actually want to already know I want to have a block of data. Now, is that realistic? So do we load a block of data, right? If you look into your assembly code of a program, you will find some loads, right? But then something else is happening, you find the next load, right? You're not loading, you're always loading a word, where you're never loading a block of data, right? But these load stores, this is what you're seeing at your processor interface. But to get to your on-chip bus, for example, maybe in between there is a cache, right? And therefore, the cache, when you have a cache miss, then the cache has to load a new block of data. And then actually the cache will basically create this request and will say, okay, now I have to load this address because this was an access, but I'm also loading a complete cache line or block of data. So give me all other information on this cache line too. And therefore, these burst accesses is something you see a lot as soon as you have caches or direct memory access controllers and so on. Okay. Now we can also go on and say, how can we even optimize the bus further? So one problem we are having is if we still have a pipelined system, right? But still what can happen is maybe you have bad luck and you want to read from a certain address, but you have a very slow target, right? It puts in wait cycles. Right? And therefore, we don't see this data coming back every cycle because we have some load cycles, and only when the data comes back, we can put the next address. We can put it in the same clock cycle, but it's still only when we got the data back, we can put the next address. And then you see, okay, the bandwidth, again, is going down, right? We only get a data word every 3rd cycle. And for that, what you can do is, you can now go and start and say, you can put more addresses, but you can put the next address even before you got the data back. So you're saying, okay, now we have 3 addresses, give me the data back, and each one of them waits 2 cycles, yeah? But the data is coming back much faster because this one, the waiting time from this one is already starting here. It's not starting when the data from the first one is coming back, right? So the waiting times of the different transactions now overlap, and therefore it goes down, as you can see here, right? So this is also a nice feature, especially if you have very slow targets in your processor or in your system, in your SoC actually. And if you look into the data sheets, so if you look like you're having a certain SoC and it has a certain on-chip bus, it will tell you, does this bus support pipeline accesses, does it support burst accesses, or does it support multiple outstanding transactions? So these are features you would find in the reference manual of your SoC or interconnect description. The next thing what you can do is, and it becomes even more complex, is, right, so if you go back to multiple outstanding transaction, still the data is coming back in order. You first get the data from the first access, then from the next access, then from the next access, right? The order is not changed. So the next feature would be something which is called out-of-order completion with interleaving. That means you have, for example, a very slow access, but then you have a very fast access, right? And then what can happen is you first put the access to the slow target, then you put the access to the faster target, and then actually a faster target returns its address, its data before the slow target returns its data. And this is only allowed, of course, if the bus can keep track of this and knows that this data actually doesn't belong to the first outstanding access, but this data belongs to the second outstanding one, right? So you have to keep track, the bus has to keep track some of the IDs to know to which address you already have put out. You want to have the data, to which address actually the data belongs to. Makes it again more complex, but as you can see, in certain situations gives you better performance. Especially if you have, again, a mix of very slow targets, which take long to answer, versus that you have some targets which are very fast to answer to your requests. Okay, good. So this was it on the single, if you have a single initiator. Now let's step up a little bit. What's happening if we have more than one initiator? So for example, we have a processor, and additionally we have a DMA controller, which also can do accesses. Then you have to go into a design where you're sharing the bus, right? And you can see what's happening here. So in this case, we have 3 targets and we have 3 initiators, right? And each initiator has an address bus where it wants to request something. It has a write data path where it wants to write data, and it has a read data bus where it wants to read data from targets. The control signals I left away in order to keep this figure not too complex. And the same thing is true, right? And each target, also, of course, only has 1 bus to receive an address, 1 bus to receive data, 1 bus to write data. And now, of course, not all initiators can drive this bus. Same problem as again, right? In a digital circuit, there's only 1 dedicated driver to each signal. So what you have to do is you have to multiplex. You have to say one of the initiators gets this bus, and this bus is basically shared between all the targets, right? So only one initiator can forward its request to this bus. So this is a shared medium which is shared between all the initiators. One of them is allowed to drive them, and this multiplexer decides which one is allowed to drive it, so which one is making the access. And for example, it puts its address and it puts its write data, or it puts its address and it waits for the read data. And who is getting the bus? This is what the arbiter decides. So you do an arbitration, and you're saying one of the initiators is allowed to have this bus, and this initiator then gets this bus and can make the access to any of the targets, right? So after here, by choosing a certain address, the initiator can select the target, right? But only one of the initiators is able to access any of the targets, and only if it is finished, then the next initiator can access one of the targets. All right, and so how would this work if we again look into it? So for example, now we have a few additional signals, so let's go through. So request 1 means initiator 1 wants to have the bus. Request 2 means initiator 2 wants to have the bus. And the grant signal tells you who is getting the bus. Here's a little bit of movement, but I think we can still see it. So let's take the first one. So there's a different ways now to do the arbitration. So one would be just round robin. So initiator 1, initiator 2, initiator 3, again 1, 2, 3. The other thing would be FIFO. The first one gets it, right? The first one who requests gets it. And of course, you can also set priorities. So there might be one initiator which is more important than another one. Therefore, if this initiator makes a request, it will be granted before the initiators which are not have a lower priority. So let's make here, we select round robin, and we're saying we have no pipelining support. That means initiator 1 would say, I want to have the bus, so it's requesting the bus, right? This is initiator 1 because it's the request signal from initiator 1. Then the arbiter would grant it to initiator 1. So this is here the grant signal would be I1, meaning initiator 1 gets the bus. Then initiator 1 would make it access, right? It puts the address, it reads back the data in the next cycle. Then what we see is there's a request from initiator 2 and again a request from initiator 1. Since we are round robin, we will give the bus now first again to initiator 2 because it's round. Then initiator 2 makes its request. And then in the next clock cycle we see, okay, 2 also wants to have the bus again and 1 also. But now actually it was the initiator 2's turn, so now we are moving back to initiator 1. And now initiator 1 gets the bus and makes its access, right? And there is no interleaving, right? So you have to wait until the data was transmitted before you can put the next address. If you have pipelining, then of course what you can do is when initiator 1 did its request, it puts the address. Then initiator 2 can already get the grant and put the address when the data is coming back from initiator 1, right? So there's this interleaving again of accesses which you have seen for the pipelining. So there is, you don't have to wait until the data is back before it can do the address, right? But as soon as you have the data, the next one can already put the address there. Okay, and this is basically how these bus protocols are working. If you have more than one initiator. So now there are, again, if you look into the data sheets of these multi-master buses, there are other features, right? So we have seen pipelining here as one feature, which works for single initiator, also works for multi-initiator. But there are now also more complex features when you have a multi-initiator bus. So one thing is called split transactions. So let's say here initiator 1, rec 1 means request from initiator 1. He requests a bus. The arbiter puts a grant to initiator 1, saying now initiator 1 has the bus. So initiator 1 starts driving the bus, puts an address. But what's happening is now also initiator 2 requests the bus, but the problem is this access at initiator 1 is very, very slow. Right? Nothing is coming back. So now the initiator 2 would have to wait very, very long. And then what's happening, and this is called split accesses, then basically the bus said, okay, I don't want to wait until this thing is finished. I now start a split. I give the bus to initiator 2. Initiator 2 makes a very fast access. And then I end the split, and then we finish the access from initiator 1. So that means if you have kind of a shared bus that something which is a very, very slow access doesn't have to block a fast access from another initiator, but the other initiator basically gets the slot in between and is allowed to do its access, and then we return to the slow access. In order, of course, again, to implement this, you have to have very complex protocols running to do that. Okay, Now, what I've said is with the shared bus, you have the issue only one of the initiator is able to do an access and all others have to wait. But that's not the way you have to do it. So you can also look into other architectures which help you to get more to parallel accesses. And the most parallel architecture is the so-called crossbar. So if you look into this, we still have each initiator, right? Driving its address, driving its write data, and reading its read data. On the other side, you have each target, which is kind of listening, am I addressed? What is the write data I have to write, or I send out some read data. And now what we're doing is, we put an arbiter in front of each target, right? So only what is shared between the initiators is this very, very last interface to the targets, because you cannot do two accesses to the same target at the same time, right? Therefore, what's happening is, for example, if initiator 1 is reading from target 1, it would request to get target 1, it gets it granted, it would drive this signal, it would maybe, if it's a write, it would drive this signal, but at the same time, initiator 2 could access target 2, because he would take this bus, and he would get the arbitration granted here, and then it could drive this and this signal, and there would be no shared medium between these two accesses, right? This one can do fully in parallel to this one, and this one could run, for example, fully in parallel to this one, and of course it also can be crossover, right? This one can communicate with this one, and this one at the same time with this one, all right? The only problem is when, for example, initiator 2 and initiator 3, they both want to access target 3, then they both have to use this last bus, right? Therefore, this is a shared medium. And then only one of them is able to drive it. And then you basically say the multiplexer says, now first initiator 2 is driving this. Then it gets its answer back. And the answer is basically here forwarded over this decoding to initiator 2. So each initiator also needs a decoder to know, to listen to the different answers of the different targets. And then if this is finished, then initiator 3 will go and start making its access to the target and wait for its data to come back. Okay, now this of course is very nice, right? So why don't we do always crossbars, right? The issue is sometimes you don't need it, right? Sometimes it's the case is if you have a lot of targets, you don't need to have all these parallel accesses going on, because often some of the targets are anyway lazy. So you could a shared thing would be better. Now what can we do is we can take the shared bus and we can take the crossbar and we can come up with something in between. And this is what is known as a layered bus. So in a layered bus you have different so-called layers, and you move your targets to different layers. So for example, here we have a layer 1 where we have target 1, and each layer gets an arbiter. So basically you have layer 1 with target 1, and you have layer 2 where you have target 2 and target 3. And the thing is, now the initiators can access targets as long as they are on different layers. So initiator 1 can talk with target 1, initiator 2 can talk with target 2 in parallel. Because here initiator 1 takes these buses, initiator 2 can take these buses, and there's no conflict. Everything is going, and the arbiter gives layer 1 to initiator 1 and layer 2 to initiator 2. The only thing, of course, is initiator 3. If they also wants to make an access, then, of course, it either has to choose layer 1, which is occupied by initiator 1, or layer 2, which is occupied by initiator 2, and then, of course, some arbitration is happening. So what you're saying is, as long as you access targets from different layers, you can do it in parallel. But if you want to access targets which are on the same layer, then you have to do arbitration, and only one of the initiators is able to do that. So a shared bus, as we have seen at the beginning, that's basically a layered bus which just has one single layer. And a crossbar basically means that's a bus where each target is on a different layer. And then, of course, there's a lot of things you can do to decide which targets to put in which layer. So this is basically, if you become a system-on-chip architect, that's something maybe you then have to decide what makes sense. Right? So which accesses should be serviced in parallel because it's good for the performance of whatever you want to run on your SoC, and which one actually you can actually do via arbitration. So the issue is this is of course cheaper than a crossbar. It has less wires, it has less arbiters. So putting a crossbar might be just overkill at some parts of your SoC. Therefore, then go with this layered design. Okay. Now, as I said, if you decide this is the protocol I want to use, and then you're designing all your state machines for this protocol, this is a lot of effort. And the kind of designing these buses is not easy. It's actually quite complex digital circuits, right? Even though if they transmit information, right? They don't do any big computation. Doing it the right way becomes very, very complex due to all this supporting of these features like split transaction, pipelining, and so on. And therefore, what people did is they basically came up with standards. So standards have two things. First of all, you can just buy some standard IP. So you can go and buy some bus somewhere which is already designed, so you don't have to design it on your own, because that's usually not a feature from your SoC which kind of makes you better than your competitor, right? You want to do like maybe a fancy machine learning accelerator, right? That's maybe something where you can say you sell your chip because it has this accelerator, not because it has some very fancy bus on it, right? So that's the one point. You can buy a standard IP, and then the problem, of course, is sometimes you also want to buy some standard other components. You want to buy a bus, right? And then this bus you want to buy a processor, and then this processor also expects to be connected to a certain bus. Therefore, you actually have to make sure that whatever bus you're designing fits with the standard interface of this processor. And therefore, basically, these bus interfaces were standardized. And of course, there are different ways of standardization. So there's, for example, one from IBM, which is called Quad Connect, and they have kind of something which is processor local bus. So these are the high-performance bus, which are very close to the processor. And then they have a peripheral bus. This is actually a more simple bus where you can connect kind of cheaper peripherals. The AMBA bus, this is the one from ARM. So you find this on a lot of chips, right? And because a lot of chips also have ARM processors. And the old high-performance bus was called AHB. This was the advanced high-performance bus, and the peripheral bus was called APB. But now actually most some cores now have this is kind of a second generation AAB, which is called XC, which you also find very often, which also come at different generations at the moment. For example, you usually have an XC4 bus on your system. And there's also ways to kind of make standards which are independent of different IP vendors like ARM, which is, for example, OCP, which is basically more of a standard where you can, it's kind of a library where you can kind of put together your bus and say this is kind of an open standard to define how your bus looks like. Okay, very good. So let's take a deeper look. So if you look into the ARM standard, right, which is which you find on many SoCs, as I said, there are these different versions. You have this AHP bus, but the nice thing now, if you look into this, you actually find exactly the features we have discussed here and looked what they're meaning, you find in the data sheet. So say this is a high performance bus, and it tells you it has pipelined, what we have looked into. It has multiple bus initiators, which we have seen. It supports burst transfers, and it also supports split transactions. While, for example, the APB bus is a very simple bus. It's very low power. It only has one initiator, right, which is actually the bridge. We will later see this. And then it's very suitable for many peripherals. And the XC, of course, that is a little bit more complex because you can configure it highly, how it should look like. So what is an example? How would such an SoC look like? So we would have the processor, which could be a high-performance processor. That processor is on the high-performance bus, right, which has this pipelining, bursts, multiple transactions. And it would be the one initiator on this one, and the DMA could be another one. Right? So this could also be an initiator. And then you would find, for example, some high bandwidth on-chip memory, which could be, for example, level 2 cache here. You can find the memory controller to go off-chip here. And then, of course, you might have some, very simple peripheral is like a keyboard, right? So if you connect this keyboard to its HAP bus, your keyboard I/O device, which is on chip, which communicates with your keyboard, that would have to have the full state machine to understand this very, very complex AHP bus. Therefore, actually, what you put in a bridge, which is basically translating between this AHP to a much simpler protocol, which is this APP protocol, and then you're driving all these very simple peripherals with this very, very simple APP protocol, and then they only need to have very, very simple bus interfaces. Because an AHP bus interface for a UART would be complete overkill. Okay, great. So I hope this gives you kind of an idea how your on-chip interconnects looks like. So now you have an idea that this here is, what you always see, these kind of errors or other depictions of your on-chip interconnect, what's behind it, that there are basically circuits behind it. The circuits have arbiters, decoders, different layers, and so on. They're running different protocols with different features. Then basically, I hope you have a good understanding of that. I think that will be helpful for you, of course, later when you, for example, reading some SoC data sheets to find out actually what kind of interconnect do you have on your specific chip. Okay, so if you are designing an SoC, you also have to think about, if you have some software running on your processor, how this software interfaces the hardware, because the software usually always has to kind of get in touch, for example, with some I/O devices to get sensor values or to write actuator values, maybe with some networking approaches when you have an IoT device and you want to send some information from the sensors via some Wi-Fi connection or some low power Bluetooth connection to the cloud in order to be able to evaluate it and so on, right? So the software usually not just runs a task without having any time of kind of communication with the outside world in the embedded domain. And therefore you have to think of how can we interface from the software different devices. And this is the so-called hardware-software interface. So now how does this look like? So usually what you're having is you're having on top your application software. That will be the software which makes the sensor read out. It might make some processing of the sensoring, some reasoning, or it might be a control task or whatever, right? And these are your tasks you're running. And this application software is then running on top of a system stack, which consists of system software. So on this system software provides communication, so access to the hardware. And it also provides a runtime environment. And this runtime environment is then provided, for example, by an operating system or a real-time operating system, very often in the embedded domain. For example, where you can schedule tasks, you can react to interrupts, and so on. And the communication then to the different devices, this is done, each device then has a software piece which is called a device driver, which is specifically designed that you can communicate with this hardware device. And this device driver then runs on top of the so-called hardware abstraction layer, and this hardware abstraction layer is kind of the lowest level of software which really does the accesses to the hardware. Sometimes if you have a very deeply embedded device, you're not trying to run this with an operating system because the memory footprint of the operating system is too large. You cannot afford to have an operating system. Then you have to kind of design your own little piece of software in the runtime environment, and this is then called a bare metal application because you basically are running on the bare metal processor without having any runtime support from an OS. Okay, so now if we want to communicate with devices, so there are different directions. The most standard direction, of course, is we have initiators. Your processor is an initiator and it wants to communicate with some hardware, which is a target, which could be a memory, but as I said, could also be IOs or some hardware accelerator you want to configure to run some computation. And what you're doing is, and we will later see this, just the target has some addresses and you're just doing load and stores over the on-chip bus to these addresses. Of course, it could be that you have more than one initiator. Let's say you have several processors on your chip. Then these processors sometimes want to exchange data. And then, for example, this can be done, for example, to have some shared memory. So there's some shared memory which is addressable by both processors. Then one can put some data into this memory and the other one can read from this memory, get this data, and then you basically have some communication between these two initiators. But it's basically handled over by one target, which is this shared memory. So the idea is that initiator itself is never addressable. If you have some kind of message passing protocol, then you have something where you basically can pass messages to other initiators. But it's a more complex setup involving hardware and software. And sometimes the case is that a target still wants to initiate some communication with an initiator. And in order to be able to do that, basically what it's doing is it can send an interrupt to the initiator. And that basically notifies it that this target now needs servicing. So you get this interrupt, and then the initiator can go to the target and look what actually the target is requiring. Okay, but the classical one is initiator to target, and we have a closer look into this one. So if you have, for example, it's initiator, a processor, for example, a RISC-V processor, which has 32-bit wide addresses, then the processor can basically address from the 0 address up to the FFFFF address, each address it can write, right? And so we have kind of an addressable space of addresses we can use. And the idea is now not behind every address you find some memory. So for example, it could be that you have some addresses which have at the highest byte 00. This would be ROM, so this is some memory, but you can only read from it. Then you have some addresses which starts with 10. This is where you have some RAM, and then this is something where you can memory you can read and write to. But then you have some very special addresses. So we have here 4 addresses from all starting with 50, going up to last byte 10. So it's actually 4 addresses, and these are mapped to a hardware accelerator. So you actually, when you write to these addresses, you do interacting with this hardware accelerator. And there could be some other, an I/O device, and this has offset of 60. Now this kind of scheme here, where you put the highest bytes is the address of the device, this is of course, you're not really very greedy with your addresses. There are very big chunks of addresses you're not using at all. If you have a really complex SoC, actually this address mapping becomes very crowded because you want to have a lot of devices you can address, and then actually you might run out of addresses, and then you have to do some fancy stuff in order to still be able to kind of do all the communication you want. So a kind of a more realistic scenario, this is taken from an ARM SoC, where you see that all the addresses from 0 to FFFFF are mapped, and they are partly mapped to memories like code, which would be, again, read-only memory, SRAMs, peripheral devices, which are then devices, then some external memory, 1 gigabyte, then a lot of things to have some external peripherals, and something which is more related to configuring the system, and a very small region where you have very specialized things like NVIC would be that you actually want to communicate with the interrupt controller of this SoC. But you can see you kind of try to make use of all the address space that this is also a 32-bit processor can offer to you. Now let's go and look into a single device. So what I want to do is I want to take one example and tell you more or less on a very theoretical basis how this works for one device. We can kind of get a kind of an idea how this communication is happening. So we have a certain addressable space we're giving to this peripheral, so this device, right? And this one we are splitting up into single registers. And the registers, the register has 4 bytes if you have a 32-bit processor. So we give it 4 bytes, and each register can be further divided into bit fields, which are subfields of this register. And into these registers or bit fields, there could be different information. There can be input data you want to write to the device. There can be output data you want to read from the device. But there can be also configuration and status information. And therefore, it might be, if this is a status, then the status is reported to you by the device, so you should never write to the status. And this can be done just the device makes this register read-only, so you're not even able to write to this one, right? Others, when you have a configuration, you want to write to it, so this might be a read-writable register. And what is also happening is, but we don't have to go too much into detail, sometimes even just reading or writing to the register will already trigger some reaction of the device. So for example, if the device gave you an interrupt and you want to find out what is the ID of the interrupt, you might read a certain status register, which is the interrupt ID register, and then after reading it, it would already clear it right away to 0. This is kind of clear on read behavior. So you don't have to go back and set it per software yourself to be 0 again. Right, so if you read it once, it expects you to know what the ID is, and then it just deletes this ID again and can reuse it for the next interrupt coming. Okay, now let's we make a quick walkthrough just to show you how this will look on the device, right? So if you really want to learn this, then just take a microcontroller and go into the microcontroller, and manually you will find all these register interfaces to different devices, and then you can go and just write some software to communicate with these devices. But here kind of the idea is to show you how the hardware, software looks like versus what's happening on the hardware side, because if you take a microcontroller board, this hardware side is kind of hidden from you. So I want to give you kind of idea also how this would look like on the hardware side. Okay, so let's take a very simple play example to get this done. So the example is the following. So this would be the function we want to implement as a hardware accelerator. So you could run this in software. This just takes the value of x and multiplies it with x, y times. So basically what you're computing is x to the power of y. Right? For example, 5 to the power of 7. Then x would be 5 and y would be 7. And you don't want to do this in software, so you don't want to spend the effort, but you rather want an external device which is not part of your processor to do this. So what you're doing is you're now creating a hardware module which is doing this computation. And here you could see how this hardware module could look like. So you would give it y and x at some inputs. Then it has a counter where it kind of counts from 0 to y. And for each, while it counts up, each time it takes x and it multiplies x with itself, with the value it's having. So this is actually we would have set here, right? Set is first set to x, and afterwards you always take x and multiply it with the value you have stored in set, and then you're basically doing the same computation which you'll be doing here, right? And in this register, so this is a register, you would have the value for set, and over the set port you can read the value of set to the outside, right? Then you also need some handshaking, so you have to be able to reset this module. You have to tell him when to start the computation. Then it has to report you when the computation has finished, so when is the result ready. And then, for example, you can also say after it has finished and you give an acknowledge and say, now I have read the value, now you can do the next computation. Right, and if you are a programmer and I did some Verilog or VHDL programming, I'm very sure you're able to design this hardware and it would be working, right? But the question is now, how do you make this hardware such that a software running on a processor can use it? And the first thing you have to do is you have to think of what are the inputs and outputs of your device, and you have to map them to addresses that the processor is seeing. So for example, we can say we want to have 5 registers, so 5 addresses basically, that the software should be able to read and write. And we start now here from the bottom, so at the address with offset. So everything is at 50, right? So at 50 and a million. So that means the 50 means, okay, I'm accessing now this hardware accelerator. And then if I make an offset of 10, at this one I can read the set value. At the offset 8 and C, I can write the x and the y value. So these are inputs, and this is an output. And then I also must be able to say I want to start the computation, and there I'm saying, okay, I have one register, but most of the register is not interesting to us. This is this reserved field. Just if I set the lowest bit to 1, that means I want to start the computation. So this tells the hardware unit, if the software sets this to 1, I want to start the computation. Then on the other side, we have here a status register and the hardware. If I read this and I read a 1 here at the offset 4, I know now the computation has finished and the value in set, I can read it, right? And since I'm ready and the set value is only read, this register is read only, while the other ones I can also write. And then the other thing is, after I read set, I can also put this acknowledge and tell the hardware device, now I have read the result. You don't have to store the result anymore for me in the set register. So I hope this became clear, right? So you say this is the mapping. Now this is very nice, but how do you implement this? So how do you know that the software is able to access this? And for that, you have to take your device. This is the device we have seen before. So this block is this block. And now you're connecting this device to your on-chip bus. And now what do you have to do, right? So the on-chip bus has a write data bus, right, where you get the data coming from the processor. And this write data you have to put either into the X register or into the Y register. I actually see there's still a mistake here. Quickly. This is the X register, this is X, and this is Y. Okay, back, right? So this is the X register, of course, is read to the X port and Y to the Y port. So if we put a value into X, and since the output of this register connected to our X port, now our device can read the value in register Rx. Same for Y, right? You can write the Y value here, and then it's available to the hardware device. On the other side, you can take the set value. The set value already is in a register in the device, right? So the device has a register where it's storing the set value. So we can just connect the output of this register to your read data bus. So the software is now able to read what it gets from set. And then, of course, we also have to make sure that we can also store the start one. So we need one single bit flop. That's only 1 bit, right? And we have to do the acknowledge. We have to store somewhere. We do it in this flip-flop. And, of course, the ready signal will also be able to forward to the R data bus, because the software must be able to read this this value. Okay, and that now means your device is connected to the bus, right? There's also, of course, some bus FSM, which understands the protocol, some address compare to know whether you want to read set or you want to read something else. So basically, it compares it against these addresses, right? What you want to do. So if you see this 10 offset, it knows you want to read set, and then this multiplexer would be set to forward its set to you. Good, okay, so now we have connected the device to our on-chip bus, right? And now we have the hardware side ready. Now we have to look what to put on the software side of our hardware-software interface. So this is the hardware side of our hardware-software interface. So what do we put on the software side? So there are different ways to design the software. And this is the so-called hardware abstraction layer. I just show you now one way to do it. So the idea is you can, for example, take a struct, and in the struct you're defining your registers. And since the struct, each one is an integer, so this is the embedded word for a 32-bit integer, the keyword, each one of them has 4 bytes, so you know that this field of the struct is at offset 0, this one is at 4, this one is at 8. If you go back, x is at 8, so if you go back, right, this makes sense because our X register is also offset 8. And then, of course, you also have to say, okay, where is this hardware located? And then you can say you define the address where this hardware is, and you make a pointer which points to the base address, right? So to your base address where your first register is located. 50 million. So now if you access this pointer, also just this pointer, right, it would make an access to 50 million. So if you make a write to this pointer, then this write to this pointer 50 million would reside in that here's an address of 50 million. For 50 million, it knows that you want to make an access on this register, which was your configuration register, right? and therefore it knows that it has to put this into these two flip-flops where your configuration is in. So this is the base pointer, but then what you do is, for example, if you want to write x, you say you take this base pointer, but you say you want the field x. Now it knows this field x has an offset of 8 in your struct, so it would say this is an axis where you put the value x in the address of the base pointer, 50 million plus 8, because it's field x. So this would take the value x and write it to the address 50 million with offset 8, which means it would write it here, 50 million with 8, right into x register. So what's actually happening is it compares the address, it finds out this device is addressed, it takes the read data port and says, okay, what we're actually addressing is Rx. So it puts the value of x into this register, and now this value x is available for your hardware device. And the same, of course, with y. This is the same thing, but the pointer of y, of course, is another offset, right? So y is in the struct the next element, and this means actually the offset is then c, right? So the offset is c, and then it knows, okay, this is y, and then it knows this y data port would actually go into this register because this register has the address with offset c. Right? This register has the address with offset 8. All right, so this instruction, if you do this, also you call this one with an integer value, you call this one with an integer value, and then we will have the value for x in this register, the value for y in this register. So this is the first thing you're doing. Then you want to say you should now start the computation. So to start the computation, what we have to do, we have to set the configuration, and we have to set the lowest bit of the configuration. So what you're doing is, in order to not modify the configuration, you're first reading the configuration from the device, then you make an OR. This is an OR operation with 1, which means you're setting the lowest bit of the configuration, and then you're writing this configuration back. So what this command is doing is so-called read, modify, write command. It takes this value, it reads it, it sets the lowest bit, it writes it back, and then what's happening is, okay, you're setting the value going here to start, so you're setting this flip-flop, so now start is going to 1, and now the device knows I have to start the computation. So what's happening if you go back to the device, the start becomes 1, then your FSM knows, okay, now I have to do all this computation in order to compute set. So now this thing would just start running and compute the value, and at some point this value set would be valid, and then it would put the ready to high. If it puts the ready to high, it can be also read back, right? So you could also set the acknowledge, but at this point we don't need it, right? Or you can also unset it again. This would be to clear the start, right? So if you want to unset it again for the next computation, so you just make an AND with this kind of with this constant, and this would just clear the lowest bit and set it to 0, fixed. Okay, but what we actually would be doing is, right, we would then, the computation has run, then what we can do is we could just check, is it ready, right? And if it's ready, right, so we are reading now the status register, and then we are saying, okay, is the status, the lowest bit of the status 1, right? So we're basically masking everything else out, we are just looking at the lowest bit, and then we're seeing whether this is run, and if this is run, we know we are ready. Then we know we are ready. So that we know that actually in set is the valid signal, right? And you can see it here, right? So if this ready goes high, we know, okay, now the value from set is ready. And then we can just read the value from set. So we're reading now this set field of our struct, and this will return us the set value. Okay, but the problem is now, of course, what if this ready returns to be false, right? So when it's not ready, right? Then we have to think, okay, when do we, then we have to go back and check the ready signal again, right? And this is called polling. So we are always checking, is it ready? And as soon as it's ready, we're taking back the result. And then basically what we're getting is already basically what you could call a simple driver function for this device, where you would be reading X, you're reading Y, then you're setting start, which means start computing, then you can unset start again, so that you got in the trigger to run, and then you're taking set, then you're asking, is it ready? If it's not ready, you're waiting, And as soon as the ready thing is set, right, so you're waiting, this is called the polling part, until the device is ready, then you're reading back sec, and you're returning set, right? So this function here would do the same as what you're doing here, just it would use this external accelerator to do it. Right? So it would read this x and y to the accelerator, it would tell you start the computation, it would wait until the computation is ready, and then it would get you this set value back, and then you have the set value the same way as here. Now, of course, this polling is not very intelligent, right? Because here the CPU is just busy waiting for the device to get ready, but actually the nice thing of having an accelerator and a processor is that the processor can do something else while the accelerator is working. So now we have to have another method to do it. And one would be that we kind of put in an interrupt. So what we're doing is we're saying start the computation. So we're setting x, we're setting y, we're setting the start bit, and then this would start the computation, and then we're just returning. And then what's happening is as soon as it has finished, it would give us an interrupt. The interrupt would call another routine, a so-called interrupt service routine. And this interrupt service routine would then basically make sure that the ready is set. And if the ready is set, it would actually set the set value. And then you have it available. So your processor can do something else. And at some point, it can check was the set value set. And that indicates, the interrupt service routine has finished. And actually, the value of set, which I'm now getting, is available. So to conclude, polling is very nice if you want to know the status, right? But of course, you should not keep the CPU in a state that's already only polling, right? This process is a very expensive resource you're having. It can do all your computation, so you should not just make it busy polling and waiting for other devices, right? So alternatively, if you have the option, you can also go over interrupts, so the processor can do something else. And at some point, it can just check whether actually these other things have finished. And then it can go and do whatever it wants to do. OK, great. So I hope this example with this hardware accelerator gave you an idea how you can connect some arbitrary hardware with your software and hook it up. And that you see that this hardware-software interface, it always has a software part, where you're writing this driver. It has a hardware part where you're taking the device and hooking it up with your system bus, so it becomes addressable from your software. And basically the interface between the two, this is this register list and bit field list where you have specified what kind of data from the device is accessible via which address. Okay, now let me give you a quick recap of all the contents we have covered now in this session of the course. We started with looking how does assembly code look like, right? And then to give us the basis to know how code is executed. And then we looked like how does C code look like versus how does assembly code look like. And we took a special instruction set, the RISC-V instruction set, which I think is a very, very hot topic. So these RISC-V processors are now becoming more widespread in academia, but also in industry. And I'm pretty sure if you go into the embedded domain and during your career, you will actually at some point then have to deal with one of these RISC-V cores and be able to program it. So having a kind of an idea what is the base of this RISC-V processes will be very helpful to you. And then we have seen, okay, if we have this assembly code, how does this get executed on a processor? And we have looked into a single cycle processor to get the idea what are the different stages the instruction is going through. And then we said, okay, this is not what we find in industry. There we actually find processor pipelines. We looked how does a standard 5-stage RISC pipeline look like. And finally, right, so if you are going more to the system level or have to do some quick exploration, whether a certain processor is capable to do the workload you're planning. We looked into ways to give quick estimations what is the execution time on a certain processor. And then we went more to this SoC aspect, so we didn't just want to look into a single processor, we also wanted to look how does this software actually be able to communicate with other devices on your system on chip to kind of cover a complete system on chip. And for that, basically, we looked first how does an on-chip bus looks like, so how can you interconnect devices, your processor to the memories, your processors to IOs and so on. And then we kind of took one example with this hardware accelerator where we said, how can we take this hardware accelerator, which is a hardware module, map it to the bus, write the software, and then this hardware accelerator is usable by the software such that we have something where some of the task is running on a processor and some of this task is running on the hardware accelerator. Okay, so I think this is not easy content. So I think we covered really a lot of content. We will now, I guess, also do these exercises and tutorials, which should give you a little bit of a better idea how these things are working out and what kind of questions you also must be able to answer in these different topics. But I think really now later, if you are in your career and you have to deal, for example, programming a microcontroller, then I hope that this content, and if you understood it, I'm pretty sure it will help you in order to understand what is going on the processor and why you see these results. So for example, why is the software written this way? Why, for example, don't you get the performance you're expecting on this processor? Right, and you can come back and look, okay, what kind of processor I'm having, what's happening on this processor, and if you have a very strong theoretical background here and understanding these concepts between the hardware and the software and how they interact, you can make very educated choices in what kind of hardware platform is useful for your application and how to best program your application to make use of the hardware you're having. Okay, then thank you very much for your attention, and I'm pretty sure that we'll be having a very interesting also interaction in the tutorials, and Alex will give you some more information on these different things, and I think then you're very well prepared to have this contents available for your career and of course also in terms of your academic progress for having this available when we have the exam. Thank you very much and have a good day.